First of all, welcome to the first knowledge sharing session in this joint industry project. Before we get started with some of the main content, I just want to go through some meeting logistics. We have at least more than 100 registered participants and expect at least around half of them to join today. We're using Teams, so please stay muted when you're not talking, and that doesn't mean that you can't ask questions. So either use the Q&A chat box functionality in Teams, or just unmute if you'd like to ask a question with audio instead. The other thing is when you present, that's for the presenters. Just a little reminder, a little bit later, is to try to use video. It's always nice to see the faces of the people that is presenting when you're presenting. And as just mentioned, the meeting is recorded, and the recording will be distributed after the call today. In terms of the agenda, we have 4 hours ahead of us with a few different items. The first hour is mainly dedicated to just a quick update on the joint industry project in general, where we are right now, what's the next goals, and what's the way forward in terms of what's going to happen essentially now between this knowledge sharing session and the one that's in the end of Q2. And then after that, we will have different companies presenting on different relevant topics. The reality right now is that we have all the data loaded in for almost all the companies, but we haven't done like in-depth analysis on the wells, which is the main objective of the next 3 months. So for now, it's basically revisiting either a few fundamental topics today, data quality, etc., or going through some of the companies that has done some analysis and to communicate those key learnings before the other companies are doing it themselves. So in the first hour of the company presentations, we'll have first one presentation by Yogashri Pradhan on ensuring consistency between multi-phase flowing material balance and the numerical RTA. Just an example from one of her wells in the Permian or in the Midland Basin. Thereafter, we'll go through a case study in the Duvernay with Jaron from Crescent Point on how they used a field-wide equation of state to map fluids consistently across all fluid windows there for 2,000-3,000 wells. Before we're going to go into a presentation with Tyler Connor from Devon to go through some items related to production data uncertainty. And there's a lot of things that's happening when we're measuring this data. It's at least good to flag and be aware of, so that those 3 presentations make up the first hour. In the second hour of the knowledge sharing presentations, we'll first have a presentation by Leslie Thompson that has been in Coterra or with Simrex for a long period of time, and he was going to go through a few, and now he's with us there at Whitson. He's going to go through a few examples with real field data of just how to interpret the multi-phase flowing material balance diagnostic plot. So that'll be a good way to kick off that session before we'll have a case study from the Anadarko Basin, where Brian and 89 have used numerical RTA on more than 100 wells there, and they've seen some key, call it practical learnings that will be very interesting for us to hear about before Braden is finishing up this session, talking about how numerical RTA or how he and how Apache has used numerical RTA to guide well spacing decisions. So that will be session number 2, and then in the last session we'll have a presentation by Tizwan from Ovintiv on just the difference between analytical and numerical RTA, where there's essentially 2 wells next to each other that is producing more similar fluids in terms of the total fluids, but the water cut are very different. So if you use analytical RTA, it can look like the total productivity of this well or the 2 wells are very, very different. But when you use numerical RTA, they're more similar, just because the numerical RTA accounts for also the water phase or the multi-phase flow effects as well. So we'll discuss that a little bit. The last thing is very, very important. It's a presentation put together by our COO, Mo, and it's about commonly observed kind of LFP trends in this numerical RTA diagnostic plot when you work with real data. Sometimes we see early spikes of your LFP or decreasing LFPs with time, and he discusses some of the reasons why we see that in practice and also what it means. So that will be a very good way for us to end today's session. So each presentation is supposed to be between 12 to 15 minutes, so pretty condensed and quick. Some presentations are even just a slide and try to initiate some discussion. So feel free to ask questions when relevant for these presentations, and then we'll at least try to tackle 2 or 3 of the questions asked, and also write all the questions down. So if there's some questions that is of importance that we're not addressing, then we can revisit that at a later point in time. As we go through this JIP, we're working continuously on a wide range of different research topics when it comes to, call it multi-phase RTA in general. And all this research, all the good and bad findings will be provided in what we call a research catalog at the end of the joint industry project. Key items or key findings of this research will be communicated in this final numerical RTA JIP course at the project end. So that's after the final knowledge sharing session. So if there's things here that you would like for us to look at that's in the realm of the key project objectives, then feel free to reach out to us and we can look at that for sure. Over to the JIP itself, just a quick progress update. For all of you, we have 31 participating companies as of right now, and we have managed to get almost all the companies to upload production data into Whitson Plus, and they're then ready to start the analysis. Between now and the next knowledge sharing session, so Q2, that's when we're going to do a lot of analysis on these different wells, and also work tightly together with each and every company in that work to make sure that we're doing that not only in isolation but mainly together if possible. And the analysis that we'll do on every single well is to define our PVT properties and create or calculate PVT properties from an equation state, perform bottom hole pressure calculations if needed, do the multi-phase flowing material balance before we do both analytical and numerical RTA, and we'll bring these results into our numerical model before we potentially will do some probabilistics and sensitivities on that model on the back end of that workflow. Just a reminder for everyone here, I know there's someone that maybe this JIP is a little bit new to. Maybe there's some of you that is following every single update we have every Friday. But just a reminder in terms of the scope of work, the main objective is to develop best practices and guidelines related to unconventional well performance evaluation in general. And we're not going to do this by only using theoretical data, but primarily using real data. And in this, in this audience here, we'll at least, and I know already we'll have many more than that, but at least have 300 wells. There's already companies that have uploaded hundreds of wells into the platform, and it's a good way for us to keep us honest when we work with real data and real uncertainties that's associated with real data. So we'll investigate how the workflow, essentially this multi-phase RTA or whatever we would like to call that numerical RTA workflow, is impacted by both well interference, reservoir heterogeneities, whether that's well geometries or potentially different fluids in different zones, and relative permeability assumptions, and we'll get back to that a little bit later. And also, if possible, generalize the workflow to consistently account for completion water. Then, of course, compare what we do to other softwares and workflows is also very important. In terms of the timeline, Q1 has been mainly to kick off the studies, get the data in there, initiate the main study objective when it comes to the proof of concept, and we also initiated all the research work. And then the key milestone is this knowledge sharing session that we have today. In the next quarter, we'll finalize these proof of concept studies. So that's performing the workflow on all the wells, and try to find out if there's some places where it really doesn't work at all. Why doesn't it work, and how can we fix it, or how can we make it work? There's another objective here where we'll try to compare this numerical RTA workflow to other workflows as well. And there's a knowledge sharing session then, and also a similar knowledge sharing session at the end of the JIP, which is in the end of Q3 2022. Throughout the year, there's also a wide range of these small courses, and they're meant to be practical and hands-on, but at least cover some key theory. So we've already had a PVT and phase behavior course, and if you were not able to participate in that course, just reach out to me, and we can provide you with the recording and the associated material, and that's also in this joint industry project shared folder that is sent out every Friday. Next up is a course on bottom hole pressure calculations. Not too many things fundamentally there, a couple of basics, but mainly how can we, in a practical settings where wellbore configurations change with time, maybe there's a mix of different artificial lifts, maybe there's bottom hole pressure data that we're lacking for a long period of time. How do you actually deal with these things in practice? So that course is coming up in the end of April. And then there's a similar course just on a different topic, which is RTA in July, and then one on dedicated to flow material balance in August. And then again, this final course is in the end of the JIP, where we'll cover kind of the key findings from the consortium. We also every single day and all the time are building in new technology into Whitson Plus, the software platform. The software platform is now around 18 months old, and we're trying to work in as many things that we see, at least that is valuable for you all, as fast as we can into the platform. The new things that's on the agenda now that we've gotten a lot of very, very good feedback on lately has been the data management part, to be able to import data in a much more flexible manner when it comes to units and also different import decks, but also to support different interfaces from public data, for instance, such as Analytical, etc. Be also able to edit this data much more graphically than how it is right now is a very high priority on our list going forward. And on a more technical side, being able to support multi-layer reservoir models from both a fluid and petrophysical property perspective, add pressure-dependent perm not only in the numerical model where we have it now, but also in the analytical and numerical RTA, and be able to tune the bottom hole pressure correlations is very high up on the list here, in addition to a wide range of other things. So for all of you, that there's a lot of you in the audience today that I know provide active feedback to us all the time. We're extremely appreciative of that. We write down every single suggestion in our backlog, and we discuss every single suggestion together as a group, and we try to accommodate that feedback all the time. And the only way we can succeed with what we're doing is that we're listening to feedback that makes your life simpler, and our life that also is using the software simpler. And that's the only thing that we care about, and we'll not settle until we've gotten a very, very, very good product that's as seamless as we hope it will be one day. So over to what we're going to talk about today. So we have around 40 minutes before we'll take a short break, and then we'll start to do the presentations, the knowledge sharing presentations today. What I'm going to try to do now is just to make sure that everybody is a little bit on the same page before we go through those presentations, because there's maybe some vocabulary that's new to people, maybe there's some repetition that's required for some of us. I'm going to try to kind of distill some of the key findings that at least I've seen, and also the rest of the colleagues at Whitson the last 3 months, in terms of when we worked with the real data here, and at least how this workflow, at least in a tentative manner, is starting to shape out and look like. And that's actually been one of the feedbacks as well from many of you, to be nice to clarify the workflow. What steps should we do when, in a little bit more explicit manner, and that's what we're doing now. The reason why I name it tentative is that, you know, it's tentative because that's what this JIP is about. We're going to try to find the recommended workflow in general. So this is of course open for iteration and changes as we go forward. But in a nutshell, kind of this multi-phase RTA reservoir workflow that we're working on and developing consists of 5 key pieces. It's PVT properties from an equation of state. Typically, for most of you, it's field-wide equations of state that were developed for most of these basins in North America. If needed, calculate bottom hole pressure calculations based on the PVT and production data, and then use production data, PVT and bottom hole pressures in a multi-phase flow and material balance exercise. And that multi-phase flow and material balance exercise is to get your contacted pore volumes that you then can try to honor when you do your RTA. So once you've done that, you do analytical RTA and numerical RTA, and you bring these results in a final output into your reservoir simulation and forecasting exercise. For many of you, at least what's a little bit new and what's the main core of this JIP, it's this multi-phase flow and material balance and RTA piece right here. And to be able to at least understand some of the fundamentals and basics that we'll see today in the presentations later today, I think it's useful that we go through just a little crash course on both of these topics. And to just get that started, it's important that we just remind ourselves about kind of the flow regimes 101 that we learned about in university, at least those of us that did reservoir engineering there. And at least cover you know, 3 key flow regimes in the context of unconventionals at least. First flow regime that we all know about is what we call infinite acting flow. That's meant for many folks also called transient flow or even unsteady flow, and that's the flow regime that ends as one pressure transient reaches one of the reservoir boundaries. And then we have something called the transitional flow, which is the flow regime that starts as the pressure transient reaches one of the reservoir boundaries and ends when the pressure propagation reaches all of the reservoir boundaries. And then the final, call it quote-unquote, flow regime is boundary dominated flow, and then that flow regime starts as the pressure propagation reaches all the reservoir boundaries. So just keep this a little bit in the back of your mind as we'll discuss these things going forward. And this is, at least for those of you that are very heavy into this space, just a reminder. The second thing that we need to remind ourselves is when it comes to RTA, like in an ideal case, what can actually be derived, quote unquote, uniquely if you had all the answers. And of course, in reality, it's subject to some uncertainty. But if you do RTA and you know the well geometry, etc., then what can you be uniquely derived from RTA? Is your so-called LFP and OIP. And your LFP, it's the linear flow parameter. That's just a fancy word, academic word for A root K that a lot of use. So we'll use these terms interchangeably throughout this presentation, but they mean the same. Okay, so the surface area generated times the square root of permeability. That's the linear flow parameter. The second is what we will refer to as the contacted pore volume. So if you're dealing with an oil reservoir, typically you talk about this as in terms of OIP. If it's a gas reservoir, it's typically the OJIP, or if you just want to be generic, it can just be the pore volume or the hydrocarbon pore volume. Okay, so those 2 things are the things that you can uniquely derive from an RTA exercise. And on a generic basis, you can say that LFP, call it productivity, correlates with 1-year CUMs, and that OIP, your pore volume, correlates with EUR. Okay, and the first part here, the LFP, is something we observed during infinite acting linear flow, and then to really be able to know how much of our tank we're draining, how large that pore volume is, we need to be in boundary dominated flow. Okay, so that's some very, very fundamental basics. So when it comes to this flowing material balance exercise, which was kind of the first new thing that we talked about or introduced earlier today, we need to have a little crash course. And we've discussed this with many of you before. This multi-phase flow material balance exercise is completely new, and it doesn't require rel perms, and it has a lot of new concepts to it, and also the way to use a diagnostic plot for those who haven't used it before can be a little bit new and will require a little bit of introduction. So that's what we're going to talk about here today. There will be several of you that will show that in actual with actual field data later today, and even Leslie will have a dedicated session on this in about a couple of hours. So when it comes to multi-phase flowing material balance in general, the one that we will discuss today does not require relative permeabilities, which is great because that's one of the key uncertainties in unconventionals. And there's some reasons for that. A lot of the details of this will be covered in that flowing material balance course later this year. But fundamentally, it outputs the pore volume. So either the OIP, the OJIP, or just the pore volume. That's what it gives us or provide us in terms of output if we do it correctly. And this you can use then to bound your RTA exercises later on. And the diagnostic plot, which you'll see many times today, looks something like this in general. Of course, it has units on the axis and it's not a cartoon, but fundamentally, this slope that you see here is inversely proportional to your pore volume. And finding that correct slope is your job as an engineer for a given well. Which means that, you know, if it's inversely proportional to OIP, this is a small OIP, this is a big OIP, and this is an even bigger OIP. What happens in real life when you deal with real data, you end up having multiple slopes. So this is just screenshots from the software. Multiple slopes that you can potentially pick, right? Because when you look at this data to the left, the blue dots, you know, you can see a lot of different slopes here, maybe an infinite number of slopes. So you need to have a framework and an idea of how will you or how should you pick these slopes. And to the right here, that's the reason why in the software you see that there's a pressure versus time plot and an associated, and that will come a little bit later here, an associated back calculated average pressure calculation. Okay, so I'll discuss that in a second. So this to the right is the bottom of the flowing pressure, and this to the right is to the left is the key diagnostic plot. And we'll look at three different slopes. First, if I draw the slope here, the slope number A, and I back out my, and this is done automatically in the software, and I back out my average pressure, I get something like this in yellow. Which on a generic basis is okay. And it's also above the measured bottom pressure, so it's at least from that perspective consistent, okay? Because you need to have a higher average pressure than your bottom pressure to be able to produce fluids. And I know for sure that in this case, we are producing fluids from this well. But if I use slope number B here, which is in this transition period, which is mainly due to multi-phase flow effects for this well, I will get the average pressure curve to the right here, which is below the bottom pressure, and that does not make sense in general. So I know for sure that this slope number B is wrong. And then I see a slope here number C, which at least in this case provide us with an even higher average reservoir pressure, which leads to this general rule of thumb for this particular plot that you should be able, or in general, you should pick the shallowest slope that you observe, which then is associated with the largest pore volume that you've observed for this well with this particular plot. Okay, and there's a few reasons for that Leslie can also address later. If you have some more sophisticated data, let's say you're dealing with a build-up data set where the build-up data is very good, if it's associated with a gauge, for instance, which we have in this case, you have even more valuable information. So if we do the same exercise in this case, we see that we draw a slope A, where we see that this slope doesn't make sense because the average pressure is below our bottom flowing pressure. Slope number B could make sense, but we also see that it actually intersects our buildup right here, and we really trust this buildup in this particular scenario. So in this case, it actually ends up being slope number C, which is the slope that we should pick, even though we don't observe that slope on the plot. The reason why we don't observe that slope on the plot is that it will take us time to really see that full tank size that this well is exhibiting. So if we let this well produce even further in time, we'll eventually see the slope on the plot. So that's why build-up data can be extremely valuable in the context of this plot right here. So if build-up data is present on the plot, adjust the slope until it honors the build-up data. This slope might be shallower, which means a larger pore volume than what the depletion data only suggests. Okay. And here it's important to remind ourselves that if we deal with a multi-phase flowing material balance exercise and we have a frac hit, then a frac hit can it's not a true buildup, so you need to be careful, and you should not use that data in a similar manner. So if a frac hit or a so-called bash is observed, this data should be ignored, and you should be careful at least to use it in the same context as on the last slide. The last thing that's very, very important when it comes to this methodology is, okay, what if our well is still infinite acting? Okay, how should I interpret the slopes that I'm looking at on my plot, or if they're in a transition period? And that's a great question. And here we're looking at a slope initially, and then during this time period, we're dealing with an infinite acting period on the plot in these blue points. And if I draw a slope on this particular plot, I get an OIP of around 500,000 barrels. If I let it produce a little bit further, my slope is decreasing, so I'm seeing more of the tank size. So if I draw a slope through this data set, my OIP is around 2 million barrels. And then eventually it will come down to the converged line right here in blue. And these are for full physics reservoir simulation runs, so we know the answers here. And this red line gives us 3.4 million barrels in OIP, which is the actual OIP in this case. Okay, so what this means for us is that, okay, if you're infinite acting or if you haven't seen all the boundaries yet, this methodology will provide you with a lower estimate of your OIP. And that's extremely valuable when you go into a numerical RTA exercise. Okay. And at least for me in general, I use it all the time to at least bound my lower OIPs. So if I get numbers that are lower than that, I know that I'm doing something wrong with my rel perms or something else. Okay, so just a conclusion on flowing material balance. Pick the shallowest observed slope, in general, the largest pore volume that you've observed for the well. And this will also in general be conservative if you haven't seen all the boundaries yet. If build-up data is present, then adjust the slope until it just honors that build-up data. This slope, it might be shallower than the depletion data, what the depletion data only suggests. And if you have a frac hit, be careful. If you develop infinite acting, then the multi-phase flow material balance provides a conservative estimate of the pore volume, and then you can use a numerical RTA to evaluate whether you're still infinite acting or not. Okay. So that's the first kind of new thing that I just want to make sure everybody's a little bit on the same page as there will be a few examples of that later today in the knowledge sharing presentations. The next new thing, which requires a little bit of basics, is numerical RTA. So most of you know what the analytical RTA is, and we'll talk a little bit about that later, which is mainly using the square root of time plot, where the slope of the square root of the time plot is the LFP or is the inverse of the LFP or your A root. In numerical RTA, the inputs are the PVT, its production data, and its rel perm. PVT and production data is either measured or calculated, with readily available data. So you might, if you don't have bottom hole pressures, you might calculate it from casing and tubing pressures over time. But rel perms is something that we very seldom have measured or that we can calculate from readily available data, and that's a problem in general. And that's why I typically advocate for using this flowing material balance method that does not require rel perm on the front end, and then try to honor that when you're tweaking your rel perms going into numerical RTA or numerical modeling exercises. Okay. And when it comes to numerical RTA in general, the basics here, and we'll not cover the theory, that's an own course, but the basics when it comes to this key diagnostic plot, which we just called the Bowie diagnostic plot, which is LFPs versus time, is that during a production period over time, when this LFP diagnostic plot exhibits a flat horizontal line, that indicates infinite acting linear flow. And as this slope is deviating below this flat line, it represents boundary dominated or transitional flow. So you're seeing either all or some of the reservoir boundaries. And of course, the magnitude of the line itself indicates the LFP for this well, or the A root K for this well. So, and for those of you who like to think about in the context of time to end of linear flow, this would kind of be the time to end of linear flow in this case. And when for those of you who run this methodology in Whitson Plus, you see that when you run it, you get your production data in black right there, and then it's overlaid with a bunch of different type curves. So that's just different simulation models where everything is the same, rel perms, fluids, etc. But the OIP or the LFP to OIP ratio is different. So you get a wide range of type curves where the only thing that's different is the size of that tank in terms of OIP or OJIP or pore volume. And here the type curve that's closest to the actual production data represents the contacted pore volume. And this is the contacted pore volume that you like to be consistent with your flow and material balance, either equal to or higher than that number. Okay. This represents our OIP, and this represents our LFP. And for those who have done a lot of analytical RTA historically with the square root of time plot, this is exactly what we've done all along. Square root of time plot provides us with our A root K, and an associated material balance exercise gives us the OIP, or the SRE, or whatever we like to call it. Okay? So actually very familiar stuff. This a little bit more hands-on. I'll just show one example of this that we also demonstrated in an SBE workshop here a few weeks ago. The reason why I like to show this is that the data is real. It's a lot of production data, and it's also available for everyone here because it's from the SBE data repository. If you use this link below here, you can get access to that data. Just drag and drop it into Whitson Plus and use that data yourself. And we're going to look at this data in the context of these 5 steps: PVT, bottom pressures, flow material balance, RTA, simulation and forecast. Step number 1 is to do our PVT work. So in the Eagle Ford, we have a field-wide equation of state developed for the Eagle Ford, developed with more than 60 PVT reports. And if you don't know what an equation of state model is, just think about it as a correlation for all fluid systems that you can use not only for black oils or dry gases, but for every single GOR, if it's near critical, condensate, near critical fluids, etc. And the GOR range that we have in this data set is from 300 scuffs per barrel to more than 100,000 scuffs per barrel. So actually spanning that entire phase window. And in Whitson Plus for this well, what I did was to go in and look at the production data. So looked at the early times kind of stabilized portion of the data right here. Ignore this early time production data or GOR data, and said that this is what's representative for my well. That number is around 750 scuffs per barrel, and I use this the so-called GOR method in Whitson Plus to predict the fluid composition. And that's a method that only asks for your GOR, and then it uses the equation of state to then predict the composition, to then calculate, for instance, solution GORs, information volume factors, bubble points, and what kind of fluid it is. And in this case, we're dealing with an unsaturated black oil. Okay. The second step is the bottom pressures. In this case, we were a little bit lucky because the SBE dataset provided us with bottom pressures. So just for consistency, we'll go ahead and use those, but those can also be calculated in the software directly. And once we have production data, bottom pressures, and PVT, we're ready to go ahead and do a multi-phase flow and material balance exercise. And what I did in this case was to zoom into the data that had good quality early or good quality data early on. And when I did the flow material balance exercise, remember the slope right here that you see on the plot is inversely proportional to the pore volume. And when I did that in Whitson Plus, I got these numbers that you see to the right. And these are the numbers that I'll like to try to honor in my numerical RTA exercise. And I also did the consistency check just to make sure that at least my average pressures is above the bottom hole pressures, which at least for all the good, what I consider good quality data is true in this case. Maybe I could even have lowered my slope a little bit here as well. In Whitson Plus, there is this associated recovery factor analysis feature that was also developed by Cimarex or Coterra that I do on the back end of this. And a few of the other authors will discuss this a little bit later. But what that requires is just a forecast of OGR and WGR versus time, and also your bottom hole pressures versus time, and it comes out with some recovery factors. And this is the recovery factors of the volume that you're contacting, okay? And that's very important for some discussions later. And it's also, you know, assuming this is an absolute recovery factor, if you're able to then lower the entire pressure in that tank that you're draining down to whatever is your abandonment pressure. And we'll compare that to some of the numerical results a little bit later. With these two steps, I'm then ready to do my RTA. And there it's very important that I keep in mind what's the difference between analytical RTA, so when I use kind of single phase equations to do my RTA, versus when I do it numerically. And the difference between analytical RTA and numerical RTA is that analytical RTA assumes single phase flow, and it assumes single phase equations, while numerical RTA, if you do it correctly, also accounts for a potential water phase if you're dealing with an undersaturated oil. Okay, which in general means that your A root K or your LFP in analytical RTA will always be lower or should be lower or equal to the LFP from numerical modeling. Okay, and the reason for that is just due to what I just mentioned, the fact that numerical RTA also account for a potential water phase, while analytical RTA just accounts for whatever, if it's gas or oil that you're evaluating. And that's very, very important to keep in mind if you're evaluating wells in a similar area, but that produce a totally different mix of fluids, either in terms of GOR or in terms of also water. Because if you want to have a consistent basis to compare productivity and completions around those wells, you should also make that kind of fluid agnostic. Because it's not fair if you say to your completions crew that you did a terrible job, but maybe they've actually done a great job, but it was only water in the reservoir, so the only thing they produce is water. And then the LFP from analytical RTA would be essentially zero because there's no oil there. But in numerical RTA, that will reflect that true completion efficiency in A root K in that sense. So if I go into my well here, quickly do my analytical RTA, I mainly focus on the slope in this case. What I come up with is an LFP of around 40,000, and I go ahead and do my numerical RTA, and I come up with an LFP of around 80,000, and also I keep honoring my associated OIP to be what I got in my flow and material balance. What's going on here? Early time, there's some crazy LFP spikes and whatnot. I'm not going to answer that now, but luckily Mo will answer that in his presentation later today. So for those that wonder about that, just be a little bit more patient, and we'll handle that later today. But at least from the consistency from analytical RTA and numerical RTA, I now have an LFP from my analytical RTA, which is lower or equal to my numerical RTA in this case. So my life is good. I feel this is the consistency that I'm looking for in general. And when I bring these results from numerical RTA, which all of you that is running numerical RTA in Whitson Plus, you can just bring those results straight into the numerical model. And this is the first run history match that you get for this particular well. A very good match on oil and gas, and also a decent match on the stabilized portion of the water rate and also pressures. And you can then add on a forecast to this well over time. And then my last exercise is that, okay, when I look at my OIPs and my multi-phase flow material balance work and recovery factors, and I compare that to my numerical RTA and numerical model forecasting, and I look at that in a nutshell over a long period of time, my EURs are very, very similar, and also my recovery factors for oil are very, very similar. So I'm getting this good and warm and fuzzy feeling because there's consistency in all my analysis. And that's kind of the thing that at least I'm trying to strive for in general, and that we're trying to advocate for in general when it comes to this workflow. And this data set is, as I mentioned, available in the manual, and you can drag and drop it and do your own interpretation, and it'll be super interesting to see if you come up with something different, or if you're seeing some of the same things as I did. The last topic before we'll take a break and we'll start the presentations from the different operators is the survey results. So thanks again for answering the survey, really helpful. And some of the survey results is more kind of FYI for us internally. For instance, what features people like to see in the software, etc. But some of them is very helpful to just go through in general, just for the entire group here to see, is there consensus around a few of these key items, or is there not? And the first thing that we asked about in the survey was what people are using RTA for. And there it was not too many surprising answers, but I'll just go through it in general. So I think what, at least the essence in general, was that they used RTA to quantify productivity. And also to quantify the contacted pore volumes, whether that's gas or oil in place that a well is draining. And that's used for well performance comparison. It's used for forecasting and maybe even validating forecasting, empirical forecasting, or guiding type curve choices. It's used for also completion effectiveness and frac optimization slash design, if you like. And then some people also mentioned that they use it as a calibration or a starting point for more advanced simulation studies in kind of multi-well simulation studies and whatnot. So no particular surprises here, but just good for us all to know. And if there's any other comments here, feel free to add that to the list. One key question that I had, at least for myself, because it was so, I felt that I heard so many different things. So I just wanted to get everybody on the same page here, is that when you do RTA and well performance, multi-phase flow material balance, whatever, you're trying to resolve a quote unquote tank size that your well is draining. And whatever, the question here was, what do we call that resolved volume from RTA analysis? Okay. And to make that 100% clear, what I mean is if you have a pad with a bunch of pore volume, producible pore volume, and you go in and you complete this particular pore volume, then you're not able to contact everything in this rock. Your wells will not be able to, or I don't think, everything that you have on this particular pad, but it will be a portion of that. And that portion of what you're contacting, that you resolve from RTA, what do we call that? That's the question. And 50% of you said that you call that contacted pore volume or contacted oil in place or gas in place for these wells. 35% referred to this as stimulated rock volume. And then the rest was a mix of other things. They used SRV and contacted pore volume interchangeably. Some called it the drained rock volume, etc. But for my purpose, it's just important to understand that there's a pore volume that we sold from RTA, and a little bit depending on what company you're working for, etc. What we call it is a little bit different, but at least in this context, we're talking about the same thing. Whatever we're trying to resolve from RTA. Another question that we asked, which was very relevant to this, was, how large is this pore volume, this contacted pore volume that we resolve from RTA compared to the actual mapped in place volumes? And that was very interesting for, at least for me, and there will also be some discussions on this later today. And what I mean here again is if you go into an oil field, you go in and you map your OIP from petrophysics, right? So you have a petrophysical team that maps your OIPs. You go in and you complete, or you drill your wells and you complete them, and then you do RTA or multi-phase flowing material balance techniques, etc. on these particular wells. How does that OIP that you contacted and that you resolved from RTA compare to the petrophysics? And almost all the answers that we got from the ones that answered the question was less than 50% in general, where most of the answers were between 20 to 50%. And then we asked the same question for gas wells, exact same number, and then the numbers in general were a little bit higher. Then they went all the way up to 80, but all the answers was below 80%, and most of them were between 30 to 80%. Okay, so not lower than that. Okay, and I think that's very important for the group to think about. And some of you hadn't done that analysis yet, and wanted to do it as well. And I think it's a very healthy exercise to do in general, because it sparks these very, very good and healthy discussions internally with the petrophysics team or the geology team, where hopefully you can kind of connect those worlds a little bit better and try to understand why are we not able to contact this even more. And I think Braden will have some good discussions on this later. A few more questions that we asked was the assumptions on number of fractures in RTA. That was very interesting. So when you do RTA, you're resolving A root K and pore volume. So of course, if you want to bring that into a realization in a history matching model, you need to make an assumption of number of fractures. And of course, that's an extremely non-unique exercise. As far as I know, nobody's small enough, at least in this room, to go down in every well and see. So it will be at least some part of speculation here when we know it's a super non-unique question, where essentially all the answers will produce the same. At least if you keep the LFP and OIP the same, all the answers will provide the same total produced fluid from the well. But 50% of the answers said that they used in general the number of clusters times an efficiency factor. They didn't. We didn't mention what the efficiency factor were, but maybe we should ask that in the next survey. But that you assume that all the clusters could potentially take fluid, but in general that there's not all of them that are taking it in, that it's an efficiency. So if you have 1,000 clusters and you have an efficiency factor of 50, then 500 of those factors are actually contributed. The 25% said that they assume that the number of fractures is equal to the number of clusters, which would then mean that you have an efficiency factor of 100%. And then the 25% was all kinds of other opinions that it was impossible to say, and there was references left and right. But at least this is, at least there's some consensus here. I also wanted to see if there was consensus when it comes to bottom of pressure correlations in general. That seemed to be a little bit more difficult. Some bias to Hagen and Brown and Beggs and Brill in general, and then 15% on Gray. And I know that there's some implicit bias here, depending on what basin and whatnot you're in. And then 35% was all kinds of other things that it was impossible to say in general, that it depends on fluid systems, etc. It depends on basin, and that you can tune the models and whatnot. But here there's was almost as many answers as participants in the survey. I think this is the last question, which is very relevant for RTA because we produce so much flowback water when we do this type of analysis, especially early time. And how do we emphasize or use this data when we do RTA? And 35% said that they ignored the early time water. So basically this water early time right here, but they tried to match the stabilized water cuts and ratios later time. And 25% said that they ignored water in their entire analysis. They didn't care about it. And then 15% said that they always try to match it and account for water in general. And then it was 25% other. Yeah. And yeah, there's two more things. Rel perm uncertainty, how people are dealing with that. That was very little consensus in general. It was primarily mentioned to be a history matching parameter or a fudge factor. There was some people that suggested that they try to keep it fairly similar and constant across multiple wells in the same region, which makes a lot of sense to me. And there was also some that mentioned that they have had success doing that in different basins. Another uncertainty is, of course, the dimensionless fracture connectivity that you assign to these models. It can be really non-unique. There was very little consensus also on that in general. Primarily a history matching parameter was what was mentioned, but many people also mentioned that they like to keep it high in general, except if there's evidence, if there's low FCD, either from analytical RTA. So if you have a positive intercept on your analytical RTA plot, then you typically can assume that there's a lower FCD, or if you have a GUR behavior that's increasing linearly, that can be kind of evidence that maybe that will be required in those cases. So that was everything we wanted to go through at this point. And before we take a small break and we'll get Yogashri to share her screen, is there any questions? I see there's a good Yeah, there's a discussion in the chat here, but there we go. Any questions at this point, or should we just take a break and then get started with the presentations? Okay, seems like everything is clear to everyone. So we'll take a 5-minute break, and then we'll get started with the presentations here in at the hour. If I just unshare my screen here, Yogeshri, can you just put on your presentation and share that so we have that ready for after the break? Excellent. Okay, so we'll get started here in 5 minutes. Okey-doke. So I think we'll get started here again. Just before we start your presentation, Yogeshri here, Curtis, if you were still there, you had a good comment regarding this percent of the well box volume that's drained. Would you like to just mention that or have a couple of comments related to that before we get started? Unless you dropped out to have a coffee.
I think you had to go to the Whitson PVT.
Oh yeah, that's true. That's true. Okay, so we can talk about that later then. But great, so we'll get started with the first presentation today. Really excited to have Yogeshri to present for us here today. And Yogeshri has done a lot of amazing work already. Uploaded more than 600 wells into the software and his machine. So really excited for her to show some of, I guess, one example workflow for one of her wells. So on that note, Yogeshri, please get going.
Sure thing. Thanks, Matthias. As Matthias mentioned already in the workflow, I'm going to present the workflow to compare the multi-phase FMB and the numerical RTA work, and I'll provide an example of how we were able to confirm some of the multi-phase FMB results with numerical RTA and what are the implications of that. As an overview of the workflow, Matthias already covered this in the JIP update, but I'll describe the PVT property input, then the flowing bottom hole pressure calculation, the multi-phase FMB, numerical RTA, the numerical model, and then the recovery factor analysis. The first step is the PVT definition, for instance. This is where I've inputted reservoir pressure and reservoir temperature, and the method that's used is GOR and saturation pressure. So using the EOS, it's also used to calculate what are your formation volume factors are, and then also you can you get to input you can also input your bubble point pressure, but the EOS can also calculate your bubble point pressure with the given fluid properties that you input. Another way to check the PVT definition is when you go through the entire workflow, and then when you notice a spike in the GOR, for instance, you can use that flowing bottom hole pressure as the bubble point pressure, and then go back to the PVT definition and re-input that bubble point pressure to make this an iterative process. That way you can refine your PVT definition. Next, you input your production data, and then you input your wellbore configuration, similar to what you do in Harmony. And then what I found really useful in Whitson is the ease of inputting the production data and the ease of calculating the flowing bottom hole pressure and the different calculations you can get from the flowing bottom hole pressure calculation. In this particular case, for all the wells that I have, I've already calculated the flowing bottom hole pressure, so this is a mere import of the flowing bottom hole pressure. Excuse me. Yeah, this is a mere import of the flowing bottom hole pressure. And I mentioned the flowing bottom hole pressure as a input because that's going to be very important when conducting the numerical RTA. Matthias already showed this. As far as one nugget of information that I picked is picking the shallower slope or the largest pore volume observed. So in this particular case, we've picked the shallower slope to identify what the original oil in place is going to be. And I found that the original oil in place was around 1500 MBO. That was calculated for the multi-phase FMB. You always want to make sure that that average reservoir pressure is greater than your flowing bottom hole pressure, and that's shown on the top right plot on in the slide. So there's a check for that, and that just gives us a confirmation that we've done this analysis correctly. The next slide I wanted to show is a numerical RTA. And after comparing the multi-phase FMB, one of the outputs is that original oil in place. So now we're comparing the output from the numerical RTA. This is the interface that is used most recently. And you check this is pretty much the Bowie or the Braden-Bowie plot, where you have the cumulative linear flow parameter and over time, and then you try to calculate over how many days, or you try to calculate based on the infinite acting flow, which OIP does it fit to the most. You can even force fit the OIP, but I usually end up picking one of the plots or one of the curves in this particular case. Another way to confirm that you're picking the right curve is, it's hard to see over here, and I can demo it in the software itself, but you can look at the cum plots too. There's some cum plots or cum oil plots, and by looking at the cum oil plots at infinite acting flow, you can calculate, or you can determine if you're choosing the correct OIP or the correct linear flow parameter and the correct OIP. This is especially helpful when the diagnostic plot is hard to interpret. These are the results from the numerical model for this particular well. We base it off of a gas match, actually, or gas rate match. And that's where we were able to get some pretty close matches with the oil rate, the gas rate, and with the water rate, and with your gas oil ratio, water cut, and flowing bottom hole pressure. As I mentioned before, at the end of the workflow, I wanted to show the recovery factor analysis, which I thought would be of value for us as a company, because when determining EURs, sometimes determining EURs using the analytical method for RTA gives you a very conservative answer because it's a single phase assumption for analytical RTA. But in selecting the original oil in place for the recovery factor analysis, what you end up doing is try matching the points for the oil rate, or for the oil to gas ratio, and for the water to gas ratio. And you click on run, and the outputs end up being the recovery factors that are on the right over here, which is about 30% for the oil recovery factor, 40% for the gas recovery factor. There was a comment made in the chat of how your gas SRV is going to be greater than your oil SRV, so that confirms this. And then it just gives you a confirmation of what the recovery factor is going to be. So since this is 30%, you're looking at an oil EUR of about 450, and then we can check that using the DCA method, which is also included in the tool. You can use the DCA method to compare what your type well curve results versus the recovery factor analysis, or versus this entire workflow, which I find to be pretty useful. And the fact that this is automated, it makes it really helpful. But that's everything that I wanted to show, and now I'm open to questions. If you have any queries about the workflow, about the assumptions used, and just about the workflow in general.
Perfect. Good on time as well. Really appreciated your stream. So maybe can you go back to the PBT slide just real quick?
Sure.
So I think what you mentioned there is also very, very helpful for the audience, that you use the so-called GOR and saturation pressure method inside of the tool. When I demoed earlier, I only used the GOR method, and sometimes like you had very good bottom hole pressure data versus time in these examples, so you could almost go into every single well and see very clearly when your GOR started to spike. So you could have almost this empirical way of picking what's a representative saturation pressure for your well. And what's really powerful with this is that then you're having both a consistent GOR, an initial producing GOR versus time, together with this saturation pressure, so you will essentially know exactly when your GORs will start to rise when you run either numerical RTA or when you run your numerical model. And these fits that you have here are very, very good. So that's the first just small comment that I have. And the other one is related to this slide number 6, just on the numerical RTA, which in this case, number 6 there, you see that there's a lot of noise in the Bowie plot itself, and you made the comment that you can use these cumulative oil and gas plots in an associated manner here, and they look much, those fits look very, very good also in this this case. But here, especially when there's so many things going on early time with this this Bowie plot, which Mo will talk about later, it can be really useful to have that oil in place number that you get from your flowing material balance as a basis when you go into this this workflow. So that was my only two comments, just re-emphasizing a few of the things you said. Mo, any comments?
There's a question in the chat also there from David that's worth looking at further. Maybe Yogesh, if you can share your screen again. He's asking about the sharp inflection point in the flowing material balance plot.
Yeah, this one.
Yep. So the question is, he wanted to see the rate and pressure versus time plot for this well to see what that corresponds to.
Okay.
Yeah. Now, basically, we can tell you, at least from our experience, it happens exactly at the pressure at which the well goes into two-phase flow in the reservoir. So once you hit the saturation pressure, once the bottom hole pressure hits the saturation pressure, that's where that happens, and that's what Narayan has had answered in the chat.
Yeah, exactly. So that's a great question from David. And in general, we see these three trends, and we also show that in the intro a little bit earlier, that you have this early time single phase slope, and then this transition period due to multi-phase flow, and then you get onto this second, if you have good data, second straight line slope. And I guess the good thing about the single phase period is because the compressibility of single phase fluid is much lower than when you have gas in the system. You'll end up seeing those potential reservoir boundaries much sooner. So there's some of the operators in this call that on purpose try to draw down their wells less aggressively to have a longer period of single phase flow, such that they can get more comfortable or confident when it comes to what pore volume as well is seeing during that period. Because when you get into that multi-phase flow period, it can take then a very, very long period of time to really see that true pore volume.
Hey, can you go back to your Bowie plot? Okay, my question is, how did you fit the actual production in there? Like, did you convert it to LFP, or it's just the actual production? So where is that access?
That's a good question. So when you input all the production data, you automatically create this cumulative LFP plot. You automatically create this cumulative LFP this plot, and you end up choosing one of the OIPs that fits with your LFP. Yeah. But particularly use the FMB, the multi-phase FMB as the reference.
I think one thing that I find very useful here is, especially in this case where we have some noisy, and that happens, like that's real life, that's real data. It's multi-phase flow effects, and there's a bunch of these things that Mo will also talk about earlier, that you have these cum oil and gas plots further down on the screen in the software, in the same feature that does not necessarily have those spiky effects in the data, that you can use in addition as a guide to come up with whatever is believed to be a correct LFP in that case. Because if you lower your LFPs, your cums will go down. If you increase them, your cums will go up. So you'll always have a lever to be able to get something that makes sense. David, you had a question there. I think that will be the last question before we go to the next presenter.
Yeah, thanks for the info about that inflection point. In a number of plays, particularly the Northeast British Columbia Montney, you have very little headspace or no headspace between reservoir pressure and saturation pressure, and you're flowing at below saturation pressure essentially from day one. So does that complicate things, make things less definitive on a material balance plot, or any comments from experience on that?
Yeah, so that's also an excellent question, David. So I think in general, the main implication is that it will just take longer time until you be able to see the true tank size or the true pore volume that you're contacting, because that you have this high compressible gas in the system. But maybe Barry or maybe Leslie or Narayan would like to provide a comment or two there. Barry?
Yeah, hi David, this is Barry. Yeah, so it won't add any uncertainty to the analysis. As Matthias just said, it will delay whenever you see the true pore volume, as those compressibility changes are happening so rapidly. It takes a while for them to settle out. Having a lot of headspace, or a lot of space between the initial reservoir pressure and the saturation pressure to play with to produce your wells above is in many ways, it's just a bit of a cheat. It allows you to observe the well during single phase flow when the diffusivity is still very high and you're investigating the reservoir at a very rapid pace. And so it kind of gives you a bit of a ability to see quickly deep into the reservoir before you start experiencing a lot of those saturation changes.
Excellent. Perfect. So I think with that, we'll go to the next presentation with Jaren. Thank you so much, Yogeshri, for an excellent contribution today. We'll go ahead now with Jaren from Crescent Point, and we'll talk about consistent fluid mapping in Kaybob Duvernay. So now, just for context here, this is very relevant for the first step in the workflow that Yogeshri talked about. Jaren, at least as far as I know, has the world record in number of thermodynamic calculations, at least when it comes to number of wells in Whitson Plus. It's like 3,000 plus. It broke the system. So he and Marcus, or Software Tech Lead, they've had some sessions together to improve that. So that's good. Even though I know there's a bunch of you that's in the thousands, 2,000 and whatnot. But Jaren he has the world record as of right now. Anyway, so Jaren has become a very good friend of mine, and also a very good friend of Whitson. Is a super user of the tool, and has done a lot of great work together with his colleagues at Crescent Point when it comes to especially this fluid mapping and making that very consistent. So super excited to have you here to present, Jaren, and I'll just let you take it away.
Yeah, sounds good. You guys can see my presentation, hear me okay?
Perfect.
Okay, awesome, right on. So yeah, good morning everybody. Thanks for the opportunity to share here. I'm Jaren Van Dyken, reservoir engineer with Crescent Point on the Kaybob Duvernay asset. Came over to Crescent Point on April 1st of last year as part of the Duvernay acquisition from Shell. So prior to that, I was with Shell for about 9 years in various reservoir and petrophysics roles, mostly on the Duvernay, but a bit on the Montney side as well. So I had a few key things that I wanted to show today. Matthias mentioned that I went a little trigger happy with getting as many wells in here as we physically could possibly do. And I think the message there is that when you make something easy, you just use more of it. So kudos to you guys for putting together a pretty slick tool. So this is just one example of what we've done with the tool that highlights how the software and the regional equation of state model that these guys have built for the Duvernay has made our lives quite a bit easier and improved our understanding of our fluid properties. So I'm going to focus specifically on the formation volume factor and how our BO model has evolved over time, as well as its impacts on oil in place and gas in place estimates. So like I said, to do this, we really leveraged the simplicity and the comprehensiveness of the bulk fluid export in the Whitson Plus software, which gives you a variety of fluid properties with only a few key subsurface inputs. So although we ran this exercise to focus on formation volume factor, we got kind of everything else at the same time. And so I've tossed a few other maps in towards the end that we're gonna show as well. So without any further ado, here's a quick view of the Kaybob Duvernay. So it's positioned in northwestern Alberta, a few hours drive northwest of Edmonton. It's a liquids-rich mudstone with significant overpressure, and in terms of fluids, it's ranging from black oil in the north to gas condensate in the south. So the acreage that Crescent Point acquired from Shell last year is primarily in the volatile oil window with some gas condensate, and it included around 250 producing Duvernay wells with around 35 kboe of production from about the last 10 years of drilling. So activity in this area kind of picked up around 2012, and Shell was one of the early players in it. Yeah, quite a number of other companies involved in this area as well. So I should mention that the Kaybob is part of an extensive regional Duvernay formation, which extends throughout most of central Alberta, though most of the activity is focused on the Kaybob area because it's the most prolific due to its high pressure and high liquids. Crescent Point had acquired acreage elsewhere in the regional Duvernay before the Shell deal, both in the West Shale Basin and the East Shale Basin, but Kaybob is currently the main focus, and we're actively drilling in the area. You can see that our land position covers nearly 13 townships east to west, and I mentioned that most of this acreage is in the volatile oil window, but as you can imagine, there's quite some variability across that. So as we move outwards from our core area, some of the other fluid windows become more relevant, and we're starting to take a closer look at what that means for fluid properties in some of those areas. So the one property in particular that I wanted to focus on today was the formation volume factor, and this slide covers kind of the various iterations of our BO model, the data that was used for each, and how the regional equation of state model that Whitson provided helped to really refine things in the fluid windows with the most uncertainty, namely the gas condensate window. So starting at plot 1 in the upper left there, we see the BO values that we were able to find in public PVT reports in Kaybob, and it's a relatively modest collection of points with limited coverage in terms of the CGR domain, but nevertheless a pretty reasonable starting point to fit with the standard BO equations. So that's what we see in plot number 2. So at that point, you're probably in pretty good shape for everything in the oil window. And it looks like a pretty reasonable best guess as to where things are headed in the lower CGR areas. But at the end of the day, that wasn't really priority number 1 to try to dial that in further at the time. So that's kind of where it stayed. And after the acquisition of the Shell lands last year, we decided to start using the regional model that Whitson had built for the Duvernay. And one of the first things we did when we got that was to see how our BO model lined up with what the Whitson model would predict. So the first step there was to load the subsurface inputs for all of our producing Duvernay wells, namely the reservoir temperature, pressure, and initial producing GOR. And then we ran the model on those, explored the fluid properties, and then when we plot the formation volume factor versus CGR, we get the data points shown in plot 3 there. So as expected, we saw pretty good alignment in the oil window, but noticed a bit of divergence as you go down in CGR. And even then, it's hard to see, the full picture since we don't have a lot of producing wells in the gas condensate window. So the next step was then to load subsurface inputs for many more well locations across the entire field, which is what we see in plot number 4. So I've kind of kept our data points from our wells in the bold colors, and then in behind there is all of the other well locations across the play in semi-transparent color. So at this point, you have a pretty well-defined BO model across the full spectrum of CGR values. And that's what our current model is based on. And I've kind of included plots 5 and 6 to compare our version 1 BO model to our version 2 BO model. With plot number 5 being consistent axes with all the other plots on the slide, and then number 6 is where you kind of zoom out and take a bit of a more macro view to see the fuller range of CGR values. So when you look at that plot 6, you might be kind of wondering, you know, is this really a big deal, and why do we, you know, why do we concern ourselves with it? And, you know, for most of our acreage in Kaybob, the answer is indeed the difference between model version 1 and model version 2 is pretty negligible, but where it does matter, it matters a lot. And I've got a few calculations on the following slide to kind of illustrate that. So suppose you have a hypothetical hydrocarbon pore volume of 10 million barrels per section. And then the question is, what does this translate into for oil in place and gas in place estimates for version 1 and version 2 of our BO model? And if you've got a volatile oil, the BO values are very similar, you know, 1.72 versus 1.67. So basically it's 1.7. And this translates into an oil in place of around 6 million barrels per section, and a gas in place around 8 BCF per section, and, you know, plus or minus 3%. The difference between the two is pretty small and definitely within uncertainty. But in the gas condensate window, you've got two very different BO values. You've got in version 1 of the model, you've got 3.3, in version 2, you've got 6. So it almost doubles. And yeah, as you can see, this translates into quite a difference of nearly 50% of in-place volumes on oil and gas, which is huge and not where you want to be in your uncertainty tolerance, of course. And, you know, at the end of the day, this might not necessarily change your estimates for recoverable volumes. So in the end, it's, you know, it's kind of a matter of what your effective recovery factor needs to be in order for these numbers to all go around. And if you've got recovery factors that are reasonable, you've probably got a good handle on your BO model. But if they're looking a little rosy or overly pessimistic, that might be a bit of a signal that your BO model is off. So that's kind of the main takeaway I wanted to illustrate today. You know, like I said, for most of our acreage, this is not a big issue, but where it is an issue, it's definitely something worth paying attention to, because it does make a pretty dramatic difference in your in-place volume estimates and your recovery factors. So I mentioned that the bulk fluid export that we used for this exercise comes with plenty of other fluid properties. So while we were at it, we put together a few more maps, and I'll just show a couple of these real quick. First one is fluid viscosity, and this is a combination of oil and gas viscosities. So in the fluid export, you've got a column that specifies fluid type, and then you've got a column for gas viscosity and a column for oil viscosity. So basically all we've done here is said that if it's a gas, pick the gas viscosity. If it's an oil, pick the oil viscosity, merge those two together, map it out, and this is what you see here. So quite a nice trend with, you know, higher viscosity in the north, which is where the black oil area is, to lower viscosity in the south, which is where the gas condensate is. And then on top of this, I quickly added a number of PVT phase envelope diagrams as well. You know, I mentioned once you make things easier, you just do more of it. So like with all the plots in the Whitson Plus platform, you can easily export a PNG of any of the plots that you're looking at. So quickly grabbed a bunch of these, put them on the map, and yeah, helps to further visualize what these fluid systems look like across the play. Again, oil in the north and down to gas in the south. And then finally, here's our map on saturation pressure, which shows you know, a bit of a local maximum extending east-west across the play, and then tapering off with lower saturation pressures to the north and to the south as well. So yeah, made some of these nice colorful maps that show the regional trends pretty quick with that bulk fluid export, and along the way kind of, you know, realize the significance and the importance of making sure that you are well calibrated for your formation volume factor models across different fluid windows. So that's yeah, that's what I wanted to share, and happy to take any questions.
Perfect. Thanks a lot, Jaron. I think there's a question from David, and I have a lot of very difficult questions afterwards.
Yeah, Jaron, Dave Sorkin with ARC here. Could you go to slide 5?
Yeah. Go ahead. Yeah.
I'm I'm not understanding how in the gas condensate case with your version 2, how the calculated OJIP goes down with model 2 versus model 1. Can you just explain the mechanics?
Yeah, so basically just taking the hydrocarbon pore volume value and then dividing it by your BO to get your oil in place, and then multiplying by the GOR to get the gas in place. So proportionally, the difference between the two values on the oil is the same with the gas. But does that help?
Can you elaborate a little bit more on the big change variation in the gas condensate BO from 3.3 to 6.6? Is that because of the two phases in the reservoir or something else?
Yeah, so that's just comparing, version 1 is what we would have predicted with our, first draft internal BO model, and then BO model version 2 is our refined version using what we learned after starting to use the regional equation of state model that Whitson's built. So that's basically the difference that I showed here. So you've got the two models. You can see the two curves. Maybe plot 5 is the easiest one to look at for that. But you got the two black dashed lines, and the one that's, if you look on the left-hand side of the plot, there's quite a difference between the two. And the version 1 model is the lower one. The version 2 model is the one that honors all of that data across the full field from the Whitson plus fluid export. So that's where there's a significant difference between the two models in that part of the CGR window. Whereas as we increase in CGR, then the two overlap quite nicely. So yeah, hence the small difference in the volatile oil window, and the much bigger difference in the condensate.
Yeah, so I think the just to re-emphasize a couple of things here, also for the audience, is and also I think what you're trying to exemplify with the calculations there, Jaron, is that you all have a lot of oil acreage, and you had a lot of oil data that you used before, and then you were kind of shooting a little bit in the blind in gas condensate, and you kind of didn't care that too much about it because it was not on your plate per se. But after you run these thermodynamic calculations, you saw that the green and these actual calculations and the actual physical measurements, there were pretty big differences there, and that's why you see this big difference on the gas condensate example that Jaron was showing there. And typically, what you see, like if you see a very lean gas condensate with 3.3 in total oil to measure volume factor, there's something very fishy. So it should be a higher number, typically higher than 4 if it's even very near critical. But you can see 50, 100 even on the wet gas or lean gas condensate side on the total oil to measure volume factor. Rohit?
Yeah, can you guys hear me?
Yep.
Okay. So did you have to input each of these points as wells in Whitson Plus? Or did you kind of have a much more efficient workflow?
Yeah, no, I had to load it. We used that mass upload template, and I think we had 2,200-ish wells in here. But basically, all we loaded in order to do this was the reservoir temperature, reservoir pressure, and initial producing GOR. So with the fluid definition method, we just used the GOR method, and we didn't load any production data or anything more specific than that. Basically, you've got a list of wells or a list of UWIs with those 3 properties. Load that, run the fluid model on it, and then bulk export that fluid export. And if it's too big, you're going to need Marcus's help to do it in pieces on the back end. But we might have fixed that in the process. But basically, that's all I've loaded. It's pretty simple. Large well count, but very little data needed to do this.
Yeah, I think that I was trying to get some clarification on that, because I think if you have an equation, say it should be just easy to generate. All you're doing is generating a matrix of initial GOR, pressure, and temperature, right, with different PVT properties. So Matthias, is there a way of actually doing this on the back end much more efficiently?
Yeah, for sure. That's what Jaren has done. So the only thing you need to prepare is an Excel sheet with or a CSV file with the well count, so and 2,000-3,000 wells for Jaren with those properties, and you just data dump it into the software and you click run one place, and I can show you how that's done as well. So then you just export it and you're done. So it's actually a very quick exercise. We've done it for many of the companies on the call as well for different basins. So if you want to do this, send me an email and we will get to it.
Okay, thanks.
Perfect. Excellent. Thanks, Jaren. I think we don't have time for more questions. I saw there was a comment in the chat that the future Whitson Plus should be able to do all the spatial mapping. Couldn't agree more, Gustavo. That's why we have GIS functionality on the roadmap. So that's great. Thanks again, Jaren, for a great presentation and to spark some good discussions there. That's always great. Next presenter up on the agenda to Dale is my very good friend Tyler Connor. If you're still there, please share the screen and show your there we go. Excellent. So Tyler, me and Tyler, we go way back. He's a very good friend of mine, and he has done some great work also in the past to communicate, I think, to the technical community that we should be skeptical to some of the data that we're delivered. Correct me if I'm wrong, Tyler, but in general, we should always assume that the data is bad before we use it, and we should find out how was it measured, when was it measured, and what are the different things that impact those measurements before we even try to touch any types of analysis and derivations from that data. So with that, I'll just give you the floor, Tyler, and take it away.
Thanks, Matthias. Can everybody see my screen and hear me?
Yeah, perfect.
All right. Good morning, everyone. As Matthias mentioned, I'm Tyler Connor. I'm with Devon Energy. I mentioned this to Matthias earlier before the call, but I got locked out of my apartment last night until like 4 a.m. So I'm working on about 2 hours of sleep right now. So I didn't get to practice my presentation as much as I'd like this morning. So in the immortal words of Bill O'Reilly, we're going to do this thing live. So walk through the agenda. As users of Whitson Plus and reservoir engineers doing numerical RTA or traditional analytical RTA, we're heavily dependent on production data, obviously. So I kind of want to go through some of the things that are going to affect this production data, in particular facilities, and the metering of our oil, water, and gas rates, and some of the things that can go wrong with that metering. And then I'll describe some diagnostics and tools that we can use that can be very prescriptive about our reservoir behavior and our well behavior as well. Unfortunately, I will not have time for that, so my presentation this morning is going to be one of sadness and despair. But I've left those slides in there, so if Matthias shares these after the fact, you can kind of run through and see what we've done with some of the things like downhole gauges and early time flowback data. So the slides will be in there. I'll just skip through them real quick once we get to them. But as I mentioned, I want to kind of take a stab at looking at facilities design. This is a pretty common design we have in the Rockies, the area I'm working currently. So I'll just kind of run through it briefly. Coming off our oil head, we're flowing into a two-phase separator. We're going to meter our gas via an orifice meter off of that two-phase. And then we'll have an oil water coming off, going to our heater treater. This is our first point of three-phase separation. So we'll have water coming off, going to our tanks. We're going to measure that with a mag meter, gas coming off again. Our oil is then sent to a vapor recovery tower. We're gonna meter that with a Coriolis meter, and you'll notice that this is our first point of oil measurement. From our VRT, we're going to tanks. But because we only have 1 point of 3-phase separation, and in particular separation between oil and water, we recycle that oil back into our heater treater. So we have a recycle pump that's going to send that back through our heater treater to make sure we're not sending water down the oil line. So that'll flow to the LACT from that point. Any gas will come off to a flare gas separator, and then sales gas separator, and finally onto sales. We lift these wells traditionally with gas lift. So we also have a compressor and recycle pump to send gas back to our downhole for gas lift. We do meter that gas with an orifice meter. So just kind of try to keep this in mind as we walk through the presentation. I'll refer to it several times as we go through. So let's start with water. It's not a product we sell typically, so we often neglect it. However, it has a lot of implications on our wellbore pressure drop calculations. It can be very diagnostic in terms of how we characterize these reservoirs. In particular, things like water oil ratio can help us understand fracture drainage areas. If you're looking from one well to another and you're seeing differing water oil ratios, potentially we're draining from different tanks. So one of the things we can do early on with flowback, for instance, is get a good description of our water. So let's grab specific gravities and salinities, because these are going to have an effect on that water density, which obviously is going to play into our pressure drop correlations, which then feed into all of our analyses beyond that. So you need to think about things like how is your water being metered? Where is it being metered? Is it coming off of the separator you're metering that? Is it when it's coming off lease and you have multiple wells flowing to those tanks? And then you have to worry about allocation issues. What type of meter? We'll talk a little bit more about some of that coming up. I want to share an example with you guys with the well that we had here in the Powder. You can see we brought this well on, and I'm showing on this plot water rates, oil rates, and then that calculated sand face pressure. So you can see kind of early on, we've got some, our water's declining. Then we start seeing this sawtooth behavior. And one might think that this is due to choke changes, but we're not seeing that corresponding behavior in our oil rates. And so what this is an iron sulfide accumulation on the pipe walls of that meter. In this case, it was a mag meter. And that causes inaccuracies in our water rate data. And you can see in future, these are pretty significant changes in our water rates. And so we implemented a program, this is during flowback, to clean those. And you see each time we clean those, we're seeing corresponding shifts in our rate upwards. And this has an effect, as you can see, on our calculated sand face pressures. So you're seeing these big sawtooths in our sand face pressures. So, so what? What does that mean for us? Well, when you're looking at a square root of time plot, obviously that sand face pressure is feeding into our normalized pressure. And what you can see is when we bump this choke, we see that corresponding rate increase in our water, and we see the change in our slope of the productivity index. We see this again when we bump from a 16 to an 18, corresponding rate increase. But then you also start seeing these changes in your slope due to the brushing of the cleaning of those water meters. And you can see that this is roughly a 1,250 barrel a day increase. So obviously that feeds into our pressure drop calculations. So this is essentially just an artifact of those pressure drop correlations, but pressure drop calculations. But if you weren't aware of what was going on, you may think that this is reservoir behavior, that this is something that the reservoir is trying to tell us. So having this knowledge of what we're doing in the field is very, very important. I'll go through a couple more. So this is another example, very similar story. We're early life, we're allocating the water based off that meter from the separator. And you can see at least these two instances where we brush the meters, and we see those hikes in the water rates. But very quickly you see it's still falling off. And in particular here in March, after brushing that meter, we saw a very precipitous drop in our water rates. And it was at this time that we essentially made the decision to change how we were metering this water. And so we started basing our allocation off of water leaving the lease. So that was measured by a turbine meter, which we've had a little more success with in this basin in terms of fouling and things of that nature. So you can see it's a much cleaner water signature here. And I mean, you can see that essentially, if you were to fit a decline through this, all this data here we can consider wrong or erroneous. But doing it this way, there's a few considerations you need to make. Are multiple formations flowing into those tanks? If so, do they have similar water oil ratios? Do they have variable water oil ratios? It makes allocation much more difficult if that's the case. Similarly, if wells are at a different point in their life cycle, if you have a parent well flowing into these water tanks and you bring on children wells, obviously the water oil ratio between those existing producers and the children wells is going to be different. So it makes, again, allocation much more difficult. Fortunately for us, the wells flowing into this pad were all the same vintage, so it was much more straightforward for us in this case. You could also implement different metering. There's Coriolis, mag, turbine. You can try water filtration or do nothing. For us in the basin I'm working, we are big proponents of using downhole gauges. So for me, I wasn't necessarily worried as much as some people may be in my water data, because I'm not having to calculate my sand face pressures. I'm used to using that gauge data. So what are some of the things we can do when we have issues like this? Well, as I mentioned, you could potentially fit a decline through it. So I knew when we were brushing those meters, so I have higher confidence in the rate data at those points. So essentially I just fit a decline through those to early time. And then what you see is when you recalculate that sand face pressure, it's a much smoother signature than what we had when the rates were kind of sawtoothing over here. You could also use water oil ratio to calculate if you have higher confidence in your oil rates. You can use those to back calculate your water. This becomes a little more difficult when wells are early in their life, because the water oil ratio is obviously changing very drastically and very quickly during cleanup. But what does this look like? So we have that same plot, square root time plot we looked at before, with the corresponding choke bumps and apparent changes in productivity due to those. But when we relook at this with the pseudo rates and that recalculation of the sand face pressures, you see a much smoother signature, and you can be much more confident in when we're looking at these changes in productivity, that they're associated or not associated with either metering issues or associated with choke bumps. So let's talk next about gas. Things you need to consider. Are you flaring? If you are you metering the gas going to that flare? The data you get at your office is potentially from sales line. If you're flaring, you're potentially not metering that gas, and so the volumes that you're seeing at the office are not really representative of what's coming out of the ground. Where are your metering points? We talked about metering off of our separator, but again, we also meter when we come on when gas leaves the lease. If you're using gas lift like we are in this basin, are you metering those injected volumes? And then if you are injecting gas, you need to make sure that the data you're seeing in your office is a net number, not necessarily a gross number. So those are all things we've dealt with in past, and I'll show you an example here of the gas rates on a particular well. Brought this well online, it's flowing. All of a sudden here in late December, we see this hike in our production or our gas rate data, but we didn't see it on the oil side. So we're wondering what's going on here. So we start talking with some of our data guys, and it turns out that a system update caused our allocation in sales meters to be added together. So we have our allocation meter, our sales meter. That data was getting essentially doubled, and that's why you see this hike here in the data. So we got that sorted out. About a month later, in mid-January, you see our gas rates start climbing again. And you may say to yourself, okay, I think I've probably reached saturation pressure here, and we're seeing, gas breakout. I had a downhole gauge, as I mentioned. So in a PVT from a nearby well, where I knew my saturation pressure is roughly 2560. So we go look at the flowing pressure of the well. It's right around 2800. So you're like, all right, potentially we're breaking out gas at this point. It's a little bit above, but it's a further distance from this from this PVT report. So did a little more digging, and I knew that recently we started lifting this well, so injecting gas, and you see that, right? When we start injecting on this well and that corresponding pressure drop, that's when we see these hike in your gas rates. And so what was happening, as you can probably guess, is that the data we're looking at is coming off of this orifice meter off of our two-phase, and essentially our injected gas volumes were not being netted out. So worked with IT again, got those volumes subtracted, and what you see is that is a result of that. It's a much smoother signature on those gas rates. Finally, let's get to oil. It's usually not as prone to errors, simply for the matter that it's the primary product we're typically selling, but there's still a lot of considerations to be had with oil metering. You have your hourly rates and daily rates, of which I've plotted both here. So you can see your dailies clearly are much smoother, where you see a lot more noise in your hourly rates. But hourly rates can be very useful, particularly like in early time flowback analysis. You have a lot more, obviously, data points between choke bumps to kind of get that trend of what you're seeing on the productivity plot. So we're looking at hourly versus daily. Again, I cannot stress this enough. Understanding of your facilities designs is very, very crucial, as we'll see in this example. Brought this well on, had some issues, had it shut in for a while, but when we brought it on, you can see this is our flowback period where I have my chokes, and when we came off flowback, you see this anomalous behavior in our rates, where all of a sudden it drops down and also becomes very, very smooth. So did some digging, worked with our field, worked with our IT guys, and what this is I mentioned this earlier, that recycle pump. So we're sending oil from our tanks back into our heater treater, and we're metering it here at the Coriolis. So what we're seeing is that we're actually metering volumes that have already gone through the heater treater. So we're doubling up, for lack of a better term right now, on those volumes. And you'll notice that we do not have, at least with this facility, we did not have a meter on that recycle line. Rather, they use in the field essentially a correlation that takes the runtime of this pump and uses that to calculate the volumes that have gone through that pump over a specific time period. But what we see is that these early and later rates were when the recycle pump, this period right here was when the recycle pump was down. They actually had to replace it. And so we're actually seeing just pure reservoir volumes at that point. And on either side, our issue is that we were seeing recycled volumes. So they hadn't adjusted what they called the K factor on that recycle pump. So we managed to work through some of those issues and started essentially implementing, this was a kind of a big fight actually, but we started implementing recycle meters on a much more regular basis to be able to net out those recycled volumes. Matthias, how am I doing on time? I forgot to start my timer.
Yeah, so we'll take a break in 6 minutes. So this is pretty good. And I get a lot of good comments in my personal chat that they love this.
Okay, well, so here's all the good stuff you can do with data. So feel free to peruse these slides on your own time, and I'll just kind of clickety-clack, clickety-clack. So conclusions. Data can be your friend if you let it. I only talked about the things I curse about data this morning, but again, if Matthias shares these slides, feel free to go look at some of the cool things we're doing with regards to using downhole gauge data to diagnose anomalous behavior and rates and things we're seeing at surface, as well as how we used it to identify artificial lift issues. I'm gonna keep stressing this point. Understand your facilities and how your data is being gathered. Before you bring on any wells, I highly recommend sitting down with your facilities engineer and production guys to really understand, hey, this is where we're going to be metering. This is where the data is going. Talk with your IT department. Make sure things like your injected gas volume is going to be netted out properly. Many of the issues I've talked about today can be handled ahead of the well even coming online. It's just having that understanding of where your potential points of error can be and just getting ahead of them. But you can't do that without a knowledge of what's going on. So employ tools that can aid in diagnostics. I mentioned briefly downhole gauges, different types of metering, multiple metering points. This is a big one. Talk with people in the field and other engineers, your colleagues that have more experience, guys in the field. They are a huge resource because they're the ones that are, boots on the ground. They're the ones going out to the wells. They have a much better understanding than, me sitting in my office looking at data, scratching my head, wondering what's going on. And finally, I'll leave you with this, and Matthias mentioned it earlier. Trust nothing. Be a skeptic. Don't just dive into an analysis before you do your homework on where your data is coming from and the validity of that data itself. Otherwise, it's good. You're going to waste your time. It's going to lead you down rabbit holes, and more often than not, your analyses are going to prove to be wrong. So with that, I think no presentation of mine would be complete without a Star Wars meme. So I'll turn it back over to you if there's any questions, Matthias.
Excellent, Tyler. I got so many good comments here in my chat. And I've looked. You presented this presentations are part of it before as well, and really appreciate someone taking that tone of voice and then being an advocate for good data and bad data and not trusting stuff blindly. So that's great. We have a few comments here just before we do the questions in the meeting chat from Barry. Great work, Tyler. This sort of things gives me nightmares. Gustavo says that the surface pressure is their main nightmare, and this is the main property for RTA. David from ARC is again saying the same things and reiterating spot on conclusions. This has been the type of thing that our 2 years of work from home may have made more difficult. You can walk down that hallway and shoot the breeze with your production engineer. That's a very good point. And then Sam also reiterates on some of these things. So that's great. I see Jordan, you have a question there.
Yeah, just kind of a comment on how the noise and rate data affects the numerical RTA workflow potentially more severely because you're calculating a bottom hole pressure. If your rate data is artificially high, then your bottom hole pressure calculation is high. And then when that pressure gets fed into the numerical model, it's going to output a lower rate. And then you're dividing the actual by the model rate. And so you end up having kind of error upwards in the numerator and error downwards in the denominator or vice versa. And so it just kind of magnifies that error, makes even noisier plots on that numerical RTA workflow.
Yeah, definitely.
Exactly. The numerical RTA workflow is amplifying those issues. So that's a very good comment, Jordan, and something we've discussed a lot offline as well. Sam's closing comment here that one of the key value cases for RTA is how it demands collaboration across functions, and this is a great example of that, and I couldn't agree more to it. And with that, I think we'll, unless there's any other last questions, I think we'll just round off the session and start again in 15 minutes. So in Houston, that is 10:15. And if you're in Denver or Calgary, that will be 9:15. We'll be back. Thanks again, Tyler. Really appreciate
Thanks, everyone.
it. Leslie, if you can just share your screen so we have that started before the next session, that would be great.
I'd like to do a mic check. Can anybody hear me?
Yes, sir.
Yeah.
Thank you.
Can you hear me, Matthias?
Yeah, loud and clear. Perfect.
Okay, so just make sure that I'm sharing this right.
There we go. See the entire beautiful presentation.
All right, cool. Thanks.
Yeah. Okie doke. So we'll get started again with the next presentation. So we have 3 presentations in this part of the knowledge sharing session. The first one is Leslie Thompson that will present on how to interpret the multi-phase flow material balance plot. Leslie has been with Cimerex, which is now Cortera, for I guess the last 10 years, and we were very lucky to have him join Whitson as an associate consultant here a couple of weeks ago. I've been very lucky to work a lot with Leslie the last year, and he and Barry developed this multi-phase flow material balance method that doesn't require relative permeabilities. And for those of you who've watched a few of our webinars, public webinars, where they've covered some of the theory, this presentation is much more related to how we are actually using the diagnostic plot in that workflow in a practical context. So with that, Leslie, I'll just leave the floor to you, and if there's any questions, feel free to ask them in the chat.
Okay, can you guys see my screen?
Yeah.
Okay, cool. Okay, so I'm going to try to go through very quickly an example of how we analyze wells using this multi-phase flowing material balance technique. And I'm going to look at a Permian parent well, production of which is shown in this slide. It's you know, as far as a parent is concerned, you can it shows almost every stage of life of a parent. So there's a couple of years where we're standalone production, then it was followed by a period where we were infilling. And then there were a couple of workovers after that. So some very, by the way, this I want to thank Cortera for letting us use this well. So some quick well facts. It's actually the first well I ever analyzed using the multi-phase flowing material balance technique. It was an initially saturated volatile oil well. The reason I picked it was because it had a bottom hole pressure gauge, so there was no problems with trying to figure out whether the multi-phase flowing correlations were giving me good bottom hole pressures or not. There's approximately 5 years of production up to today. 2 years as a parent well, and then it was infilled, and then there were 2 subsequent workovers. The last talk I thought was excellent, and this is a good example of where we had a well, and the water production data was always questionable. The oil much less so, and probably the gas. For this particular well, at the beginning, we thought that the initial water saturation was about 30%. So I'm going to step through how we looked at this well at the beginning, and then I'll show you how we look at it over the entire period. So I'm going to look at the early production period. And actually, when I first started looking at it, I only had 500 days of data. But I'm going to look at the first 600 days of data. And I'm going to show you what happened when we analyzed it with an initial water saturation of 30%. So if you plot all this data into Whitson, this is kind of what you get out of it. I'm going to go through all of these little plots in a second, but basically the big plot here is the multi-phase flowing material balance plot, the main one. And as Matthias said earlier, we usually look for the lowest slope. This is the slope that I picked, and I'll show you a little bit more about why that is in a second. So if I zoom in on this, there's a couple of things that I want to look at. The first thing is that usually Whitson doesn't show you the average rate normalized density plot, but I like to put it on. That's the purple line here. And if everything is fine, it should be going through the origin and should be parallel to the line that you picked. And all the wellbore points, all the blue data points, the wellbore data points should be plotting above that purple line. The purple line you can think of as the ideal line if this reservoir was indeed producing as a tank. In other words, if I took that reservoir, I completely shattered all the rock and joined it by infinite conductivity fractures and started producing it, then from time zero, it would be initially in it would be immediately in pseudo steady state And this is the response that I should get. A well response, a real well response cannot be better than that. If you find that you have periods of data where this blue line is definitely falling below the purple line, it tells you something's wrong. Either your pore volume that you picked is too small, or that you have pressure support from somewhere else. Something's wrong. It's not behaving like the tank that you think it is. In this particular case, all the bubble pressure is more or less above the average pressure, so everything is fine. That looks good. The early part, you have a shallow slope here, and in earlier presentations, I saw people say, well, this is a good indication of what the pore volume is, and that is true, provided the reservoir is undersaturated. So if you're dealing with a pure liquid, for example, reservoir, it's above the saturation pressure, you expect that you may see the reservoir boundaries a lot faster than you would in multi-phase flow, and you'd see this early time slope. So you look at the slope and you say, well, maybe that is what's happening here. But this reservoir was initially saturated, and that means that there was initial gas saturation there as well. And the question is that real, or is that just due to water rate quality? So I'm going to come back to that in a minute, or in a few minutes, and so just bear that in mind, okay? So the next thing that we look at is the average pressure and the well pressure plots, and Matthias did a really good introduction to this in the beginning. And in this case, the average wellbore pressure is always above or equal to the wellbore pressure. So again, that's a good thing. That looks fine. Then you go to the water saturation plot, which is something I really like to look at. And we said that the initial water saturation was 30%. And if you look at this over 600 days, that water saturation has fallen down to something like 7%. The question is, really, do you really expect this to happen? There's only two ways that water can be produced from a reservoir. One is by expansion, and you don't expect much water from that method. And the second way is by displacement by hydrocarbons. And these are layered reservoirs in many cases, and the probability of this happening in real life is so small that it's very unlikely. So when you look at this, you have to ask yourself, is this real? Okay, so looking at this, everything seems fine except for that huge change in water saturation. And now you have two paths forward. First path is you could go back and you can talk to your petrophysicists, your geologists, your completion guys to try to reevaluate that initial water saturation. And that could take some time. The second way is to just take water out. And I'm gonna look at both of these methods because we actually did both of them. So reevaluating the water saturation, we started to ask ourselves, where did the fracks penetrate? Is it possible that those fracks could have grown out of where we thought they grew and maybe into some water-bearing systems? Or is it possible that some of the water-bearing streaks that we saw on the logs were actually productive, but we didn't count them? And so when our team looked at this, they finally decided that probably the initial water saturation should be bumped up in this well to 70%. If you redid the whole analysis with this 70% initial saturation, nothing much changes. I mean, it looks more or less the same, except if you look at the water saturation plot, now it makes a hell of a lot more sense. It goes from 70 to maybe, 62, 63% over the 600 days. And that feels much more reasonable. I'm not saying that the answer is, I'm not saying that our assumption is correct. I'm just saying at least it makes more physical sense than the very first assumption that we had. So the second way that you can look at this is say, hey, I'm not even going to worry about water. Okay. If you do that, then the mass of the water in the tank is going to remain constant. I'm not even going to consider water production from this tank. The water in the tank is assumed not to expand. The water saturation, therefore, will only change if the reservoir has rock compressibility. Otherwise, it's going to be dead constant. And then the nice thing about this is that if you have poor quality rate or water rate data, which I think we did in this particular case, it will not affect the plot since we're actually excluding all water from this whole thing. It turns out that this, if you do this, it's going to provide the most conservative estimate of the hydrocarbon in place. And I'm going to compare all the numbers that we get from these different analyses at the end. So you'll see how the numbers change. Okay, so if you take the water out, the first thing you notice is that it cleans up the wellbore pressure data quite a bit. The wellbore data quite a bit. And you also don't get that first shallow period at the beginning. And so that first shallow period was more than likely due to bad water data. Other than that, everything looks good again as far as these two plots are concerned. If you look at your average pressure plot again, it's fine, and water saturation plot, as you would expect, is more or less dead flat. In fact, it actually is inclining a little bit up because this reservoir, by default in Whitson, has a small rock compressibility. It's 4 by 10 to the minus 6. Okay, so now I'm going to take that analysis and I'm going to say, well, let's look at the entire 5-year period. And this is my fit that I had. The black line is the fit that I had on the original set of data for 600 days. And I simply took a bunch of parallel lines to that initial slope, and I started moving them around on the plot. So for the infill wells, you actually have 2 periods where you see the flat period with the slope approximately equal to what we picked at the beginning. So that's the infill in blue. And then for each of the workovers, we also get the same slope repeated. Okay, so that's kind of nice. It shows that for this particular well, a bunch of things happened, but eventually it always came back to the same pore volume. Now, that doesn't always happen in a parent well. It just happens in this one. Sometimes in parent wells, when you do infill, they will lose some of their drainage volume. Sometimes they may actually increase, not too often, I guess. But anything can happen. It just happens in this particular case that happened. The drainage volume touched by the well was more or less retained. If you look at the pressure plots, now you have this huge peak in wellbore pressure, the bottom hole pressure gauge. The question is, should you try to honor this? And the answer is no. You should not. This is from a batch. This is from an external pressure source, so you should not try to honor this. And so I'll keep the volume that I picked at the beginning. The other thing that I look at here is if you had keen eyes, I guess, and you looked at the very first plot that I put up, you notice that the line that I picked, the black line, is not parallel to the purple line, the computed average pressure line. And the question is that okay? I mean, I said that for an ideal tank that, the plot, that the purple line should be exactly parallel to what I picked. And it's not okay. So what's wrong here? Well, the problem is if the average pressure plot, the purple line, is too steep, it means that your rock compressibility that you picked is too large. On the other hand, if it's too shallow, the rock compressibility is too small. So in this particular case, the average pressure plot is too steep, which says that the rock compressibility that Whitson picked, the default value of 4 by 10 to the minus 6, is actually too big for this reservoir. And if you just redid this and took compressibility out, again, this is still with no water, you see that the lines become parallel again. Okay, so now if you look at a comparison of all the different methods that we use, what you see is that for the initial volume that we initial water saturation that we picked, we get the highest oil in place, and then with no water we get the lowest, and then what we have now for our estimated water saturation is somewhere in between. So that basically concludes my my presentation. If you have any questions, I'd be happy to try to answer them.
Thanks, Leslie. There was a question here related to the initial gas saturation. There was actually some initial gas saturation there from a PVT perspective initially, so it's not a single phase initialization. Can you just comment that real quick, and I can provide a few cents on that too.
That was the initial gas saturation is straight from the Whitson PVT module. So we put in what our initial GOR is and API and so forth, and you guys told us what you thought the average initial gas saturation was, and we took that as Bible. You are the PVT experts, we are not.
Yeah, so just basically to Braden's question, there's just an output from the per mean equation state model. So if you have a pressure that's lower than the predicted saturation pressure, you'll end up with a initialization that's two-phase, and that's something that the software deals with very well in the numerical model and multi-phase FMB, wherever else it is relevant. Then that's something that we've observed a few places in the Permian, mainly on the Delaware side. Also many places in the Montney and also in the Anadarko Basin. And we've also seen quite a few, a subset of PVT reports of the 500 to 700 PVT reports we now analyzed in shale North America. Then we've seen that in many of those reports as well. Gustavo has a question. How can we justify the water saturation being 70 going all the way up from 30 if petrophysical data has shown 30? And then I think for the clarity here, I don't know if the petrophysical data showed 30 in this case, or if you can provide a little bit of light on that, that would be great.
Barry, do you want to talk about that? You're much more familiar with that. I know that the initial value that people chose for this field was 30%, and that was just across.
Yeah, so this is a very very old well, and it was analyzed originally before this company had a detailed petrophysical model across the basin, and most of these initial water saturations were just ballpark estimates based upon downhole relative rate. So that initial estimate of 30% was never a good estimate that was tied to anything.
Great. And then Raj has a question. So with infill wells, we did not see any change in affected OYP, although there was some noise in the decline onset to offset wells were drilled. So I guess, would you like to comment that real quick as well, Leslie?
Okay, so if you look at this plot, is my plot still up on the screen?
Yep.
Okay, so if you look at the plot, there's a bunch of crap below the average pressure, the average density plot, and all this stuff is happening, right after the infill. In fact, many times when we do these infill fracs, you'd actually see a distinct line with a much lower slope than what you picked at the start. And my interpretation of that is that when you start the fracking process, you join up all these fractures with the parent well and the infill wells. And for a while there, the parent well seems to see something a lot bigger. Okay, so it's draining not only its original area, but maybe area that was also exposed during the fracturing process. But that goes away after a while, and this particular well went away, and eventually it came back to what we have here. So this region that I have here, and in this particular case, there was no, you could probably say that I could have fit a line that was steeper through this infill data, which would suggest that it saw a smaller volume. Or you could also say that perhaps this line that I drew that was parallel to the first was also parallel here, so it saw the same volume. I tend to think the latter, simply because after the other workovers, the slope did indeed come back to what I saw initially. So in this particular well, it seems that the fracking, the infill process, did not significantly affect its original, the original estimate that we had of pore volume. And that's not always true. Okay, as I said, in many cases you'll see a distinct drop in pore volume, and that remains permanent. So I don't know. Barry, do you want to say anything more about that?
No, I think that's great. That this particular example was a well that did not see a reduction in productivity, long-term productivity, after it was offset. There is a comment or question here about any comment on the impact of frac load water on these calculations and plots. I'll go ahead and try to answer that and then let Leslie expand upon it. That's something we have spent a great deal of time debating and thinking about. And I guess the short answer is it depends on the system. This particular system is a very large system with a lot of water. As you can see here, he's estimating over 10 million barrels of water in place. And so in terms of overall pore volume estimates, as long as the water rates are measured accurately, backing out the frac load from that is doesn't create too much error in the analysis. As you can see, if he completely excludes water, the difference in his entire pore volume estimate goes from like 2.1 million barrels to 2.3 or 2.4 million barrels. It's fairly small change there. And that's just associated with the fact that this is a very large system with a lot of water.
Yeah, that's correct. I don't think I need to add any more to that. All the analysis that I showed for the entire thing excluded water. So that helps a lot with removing uncertainties in water pressure measurement, water rate measurement. And it gives us a more conservative estimate, as I said, but it's not unreasonable.
Perfect. So our time is up, gentlemen. We thank you a lot, Leslie, for this great presentation, for also showing some of the practicalities and some of the real life implications of being in the real world with workovers and infills and bashes and whatnot. So that's really appreciated, and thanks again, and also thanks to all the questions and for the comments from you, Barry, as well. Next up, we have Brian Collins from 89 Energy that has applied numerical RTA for 100-ish wells or so in Anadarko basin, and we'll communicate a few key learnings, just key practical learnings from doing that work the past year. So I'm super excited myself to see some of this as well, Brian, and it's been also a lot of fun to watch you become like a what we would call a super user of the software. So that has also been really appreciated, and thanks for all your good input. So just take it away.
All right, thanks, Matthias. You guys can see my first slide here.
Indeed.
Okay. Yeah, hi, Brian Collins, Senior Reservoir Engineer at 89 Energy. I've been here for about 5 years, working almost strictly Anadarko Basin, and I worked along with some of the other people from other companies on this call right now at Lynn Energy, also in the Anadarko Basin. So I've got a fair number of years of experience in this area, and last year when we took over an asset from a couple of other portfolio companies, I had been using Harmony for a long time, and I found that we got the PVT module from Whitson Plus as a benefit of one of the companies that we took over for. And Matthias started talking to me about the numerical RTA process, so I gave it a try and quickly realized what I believe to be its superiority compared to an analytical RTA solution. So as a little more background for the area that we're working, we did assume operations of around 70 operated horizontal wells that were drilled primarily by Casillas and Native in the last half decade or so. This well set had a pretty clean amount of data. It was a lot of downhole pressure gauges were run. We had good hourly flow back for most of the wells, and so I appreciated that aspect of the asset. One of the difficulties was the number of parent wells versus infill wells, because all the parent wells had pretty much been drilled to this point think parent wells can be really difficult, and especially in this area, to figure out how to translate into what the well performance will be at an infill situation. Most of the wells that I've done this process on now have been oil wells, or like I said here, at least if they were at saturation or above saturation pressure. The area that you can see on the right, the South Scoot block, is primarily the Golden Trend play, and it is, especially in the Woodford, characterized by depletion from all the faulting and fracturing that's happened in that area. And so I'll get into it in a little bit, but I found it very difficult to actually use the numerical RTA workflow on those wells down there. In addition to our operated well set, we do have a very extensive non-op well set. Of course, as non-op well sets go, the quality is of varying degrees. And I wanted to put a quick shout out here. If you're in the Anadarko Basin and you want to do any sort of data trade with me, I'm all ears all the time. So just hit me up after this. And so right now, our current operations are that we're infill drilling throughout the whole area that you see defined on the map, and typically with 2 to 3 child wells in addition to the parent well that's already there. And we may try up to 4 child wells depending on some further work that we're doing. So to summarize what I'm going to talk about in this presentation about kind of what I've learned going through all these wells in the numerical RTA process. The first and foremost is that for me, it's really changed the way that I think about what the reservoir permeability is in both the Woodford and the Mississippian. I had come into RTA with some sort of preconceived notions about unconventionals in general, and using numerical RTA really just drastically changed the way that I think about just the overall SRV model, but then also the actual reservoir properties in this area. Secondly, here I've got that relative permeability. I never really had to pay attention to relative permeability before. I was always using the analytical RTA and just didn't even really register as something that I needed to work or to think about. And luckily, through the whole process here, I've found that I can use a pretty consistent set of relative permeability numbers, Corey exponents, that is. The numerical RTA method, it has given me a nice way to compare well to well. I think, again, going back to the analytical or single phase model, you never felt comfortable comparing the productivity of a gas well to an oil well, and then all of the, the PVT range in between. It's just kind of changed depending on which phase you were primarily modeling. The numerical RTA, as I mentioned, tends to break down a little bit in areas where you see a secondary reservoir component in your PVT. It's tough for me to say sometimes whether it's a depletion issue, like I mentioned down in Golden Trend, or if in fact you just have secondary gas sourcing. But the numerical RTA, and for that matter, the flowing material balance, when you set it to a certain GOR that you believe in for your initial producing GOR, and then you do some decline curve analysis, or any of the number of reservoir engineers in your office does some decline curve analysis, and the gas it says it's going to produce is double what you're getting from your model, you recognize that you have an issue there. The comparison, though, of successful history matches where I don't have that secondary gas component, it has let me be able to look at what the total mapped oil in place is versus what my SRV oil in place, and generally be able to predict how much we're going to be able to exploit in a given unit. All right, so I'll move on here. Okay, so getting back a little bit into what I was talking about in my former use of analytical RTA models, I'm going to just kind of compare and contrast how that paradigm change really has taken place. So going through the analytical RTA process, it is useful for, and I've used it in the past for comparing wells of a similar fluid type. SRV models that I've used in the past, I sort of fit the cluster efficiency as well as half lengths, believable half lengths, to what I thought were reasonable estimations of permeability. And so when you did an interpretation of the end of linear flow, kind of as if everyone has read Braden Bowie's paper, when I was one of those engineers that just put the line right on that slope change, I was getting permeability estimates that I believed in by adjusting things like cluster efficiency and so on. The EUR estimates that I would get using that model, I never believed them. They always appeared to be far too low, and I didn't at the time really have a way of understanding why all of that was happening. So for my analysis prior to using numerical RTA, I more or less just threw out any sort of EUR estimation. Again, as I mentioned, never really paid attention to relative permeability. All I was really using the tool for was comparing productivity of well to well in, again, a similar PVT range. And then, as I mentioned, I kind of assumed a permeability value that I thought was reasonable in that range that I specified here, and tuned my model thus. So moving on to numerical RTA, it has been actually very useful in comparing the A square root K values, so the productivity, across lots of different fluid types. Feel pretty confident in my ability to do that now, whereas I didn't before. What I have found very interesting is that when you let the model do what it's going to do by constraining it to the GOR profile that it has, as well as the, well, primarily the GOR profile for me, which includes both the linearity of that GOR profile. It gets you to where you can sort of fix down what your permeability range is. And as you see here in the notes, I've gotten much lower on what I thought was a reasonable permeability estimate. The other really interesting factor there is that the cluster efficiency, I had always kind of just messed around with it, but assumed it was probably somewhere in the 50 to 70% range. The cluster efficiency, I believe now, is almost exclusively 100%. And the figure that I included to the top right, I know those numbers are a little bit hard to read, but the preponderance of permeability estimates end up being down at that very low range. And that's, and in all of those cases, that's assuming 100% cluster efficiency. And I think what's really interesting is that it works whether or not you've got wide cluster spacing or you've got very close cluster spacing. In our wells, in fact, actually the one place that it didn't work for me in the past was when I mistakenly believed that a set of wells that I was looking at had double the number of clusters, but the only way to get the permeability to make sense was by having them. And then I found out later on that in fact they were fracked with half the number of clusters, and so that model worked again. And then, as I mentioned here, I do use ResFrac a little bit, and I've been able to successfully simulate being able to get about 100% cluster efficiency at the close cluster spacing that we pump in real life. The EUR estimates from numerical RTA finally show a high degree of agreement with what I would call a reasonable decline curve analysis estimate. And then where it works for me, which is few and far between, unfortunately, the multi-phase flowing material balance. I think that may also, after watching some of these presentations today, that probably is partially some user error. And then, as I mentioned before, gas and oil relative permeability, I've had to tweak it considerably from a 2 and 2, but and it's now actually closer to a 1.5 for gas and about a 5 to 6 for oil. But I find that it works over and over and over again in the wells that I simulate or model. Okay, so the bumps along the way, the things that I've had struggles with in numerical RTA, some of them have been worked on and fixed in the way that the workflow works, and some of them we still have yet to fix. Whitson's been really great about implementing some changes that and I'm sure others, not me exclusively, have asked for. But anyway, I'll go through a little bit of that. The first problem that I had was using that numerical RTA workflow. I have almost across the board wells that have very, very low fracture conductivity, at least very, very far from infinite. And so you can see in this plot on the right that the cumulative oil plots that I would get almost, if I don't start really cranking down on the fracture conductivity, they almost always look very linear compared to what the model wants to spit out. And so luckily, almost as soon as I started using Whitson Plus, they fixed that in the model. But it has made, even now, when I can use the quicker workflow rather than having to change all of the simulations manually, that is, it still requires a lot of iteration. However, the upside to having that issue was that it made me aware that we do in fact have very low fracture conductivity throughout all of our wells, and so it's helped me to put together some of the dots with why we have such a strong fluid loading versus productivity correlation in our operated area. I think it's my personal belief is that the Woodford and the Mist, to a lesser extent, primarily the Woodford, is highly fracture driven, and the question that has become that this analysis has let us do is, can we drive that fracture creation without having to drill a lot of wells? Can we drill fewer wells and just frack them with higher amounts of fluid? The other issue that I have had and I'm still having is this issue of being unable to model GOR in some of the more complicated wells. In the plot down to the right, you can see that this well in particular moves from around 1,000 GOR over the course of 3 years or so up to around 80,000. And this is not even as exacerbated as some of the other wells that I've got. This is my attempt to get that model to fit. And you can see that down at the bottom right where I circled, the black intercept on the y-axis is actually around 2,000 or 3,000 SCF per STB. And I still can't get that, that line to fit over the course of a long period of time. So going back a little bit to what I was talking about, I think that it's probably a fair statement here that we exist in a 2 PVT model system. The nice part about this is that it's let us know that we have to think about our volumetrics a little bit differently. We don't have a single phase model that we can put in a box and create OOIP numbers for. But I'm still looking forward to, I think Matthias has talked about doing a 2-layer model. And so I'll be thinking about how to implement a dry gas layer into coupled with a black oil model in that situation. It does obviously become very, very non-unique at that point and makes it a pretty difficult problem to think about. And as I mentioned, I've had struggles with multi-phase flow material balance. In these cases, I'll start my GOR at 1,000 SCF per STB, and then when it looks at the flowing mass, it's like, oh well, your reservoir has starting out with 10 million barrels, and your recovery factor is going to be 2%. It's hard to believe that. Okay, lastly, I'd like to talk a little bit about how we've used the numerical RTA to inform our full development studies, and then what we're actually doing in practice. The question that I came up with pretty quickly was whether or not I could look at the SRV generation numbers that I now believed in these wells, thanks to a more rigorous process, and compare those to the mapped oil in place. And then if you could do that, could you understand at what sort of percentage of that combined volume are we able to exploit with a certain number of wells? And then the question then also becomes, can you exploit more of that OOIP with more wells? Do you reach a point at which you hit a strong diminishing returns relationship? And then also, can you do what I kind of alluded to earlier, which is to decrease the total number of wells, but increase the frac size and have a higher degree of capital efficiency? And as a little bit of background, our shop is the primary economic driver that we look for is not rate of return, it's discounted ROI. So while that discounted, or while your near-term production does tend to affect your discounted ROI to an extent, it's not as strong as simply your EUR. So we are very EUR driven here. You can walk you through these cases that we've got over here. You can see the results, but in each case, I've got the total thickness of the reservoir for the Mississippian and the Woodford combined, the mapped oil in place, the total SRV generation to include a parent well that I've identified, as well as trying to, take out what portion of that parent well's SRV I believed could be reasonably attributed to outside of that 1 mile east and west. So then the number of reserves exploited is simply taking the SRV and dividing it by the OOIP. And after that, we've got the EUR for all those wells. This is a little bit of a weird subject, but I did include the kind of the initial EUR for the parent well, assuming that that's sort of, even if it gets disrupted later, it's sort of, and it's not necessarily going to be easily exploited by the children wells, in my opinion. And then the calculated SRV recovery factor is just the EUR divided by the total SRV. The EUR per lateral foot, simply taking the EUR, dividing it by the number of total lateral feet in all the wells, and then the cluster spacing pumped on that well, as well as the fluid loading. And so you can see that we've got a smattering of cases here, some drilled in both the Mississippian and Woodford, one in the case of case 3, where it was only Woodford, and then in case 4, you've got a combination of Woodford and Miss again, but fewer wells. Some of the observations that I can make here and that have driven some of our operational decisions are that for full disclosure, case 4 is one of our cases, one of our pads that we've drilled. And I think that this does indicate that the higher capital efficiency can be obtained from reducing your cluster spacing down. You'll see in that case, it's 10-foot cluster spacing, as well as increasing your frac loading, but giving the wells some space from each other. Right now, those wells are producing like parent wells. They're in the case of case 2, where you see very many wells drilled over the 1 mile range. This is, keep in mind also those numbers are for a 640 acre unit. I tried to specify that above. There may be some aspect of poor geological quality in that area. I don't know how strongly I believe that, but it might be an aspect. In any case, you can see that at the 22 barrels per lateral foot, we've obviously crossed over the line of diminishing returns in that case. Case 3, I think, is interesting because I think it points out that your SRV generation is significantly higher in lower amount of rock than in case 1. And this may, I think, point to just the generally easier SRV creation that you find in the Woodford throughout this area. We've actually we've begun to move from a combined Mississippian and Woodford program to strictly drilling in the Woodford, at least in our central area that you can see circled in the plot below. That's all I've got. If anyone's got any questions, I'd be more than happy to answer them.
Great. Really, really interesting, especially this last stuff, Brian, and very relevant for the survey, and I think also for the next presentation. We'll only do one question now, and then we'll leave the other questions to Braden later. There's a question from Gustavo there, if there's any learnings, and I think you addressed it here in the last thing, but like any particular learning that you've kind of derived from this numerical RTA that has helped you to guide well spacing either one or the other direction?
Yeah, it would just be, again, looking at how your total SRV generation increases or decreases based on how many wells you're fracking in the area, and trying to account for the variations in your completion. It's so hard to argue in this area with how strongly production, in primarily EUR in this case, is a function of your fluid. And so if you making sure that you account for that, it does require thinking in a couple of different directions at the same time. But yeah, that would be the primary way. The LFP / a square root K argument here, it's still a something you have to look at. You certainly like to see your IPs, but these wells are such low fracture conductivity that even if you generate a massive fracture area and that is recognized in that a square root K calculation, it can be difficult to ever realize the near-term production from that.
Yeah. Perfect. So just while we switch presenter here, so thanks again, Brian. Excellent stuff. We're a little bit behind schedule, so if Braden, you're the next one up, you can go ahead and share your screen. We'll take a little bit shorter break after Braden's presentation. Just as a little fun historical note, so last year when Brian started to use numerical RTA, one of the first things he asked about was how to incorporate low fracture conductivity in numerical RTA. And it sounds simple, but actually when you go from one kind of template model to another one in a generic manner, it's actually not very simple to do that conversion. And it was actually Braden that sent the recipe of how to do that very consistently, and we included that in this paper we had together, Braden, myself, and a few other colleagues at Whitson that we presented at ATC last year. So everything is kind of connected here, I feel like. And with that, thank you again, Brian, and the floor is yours, Braden.
Sounds good. Thank you, everyone, and great presentation there, Brian. I actually wish maybe I could have changed mine after seeing yours, but I'll definitely have to touch base with some of your findings because I think we see some similar things. But so for everyone, my name is Braden Bowie with Apache. I'll be talking today about a lease that we have with 7 wells that we did a spacing trial. So comparing the LFPs and the OOPs we generated and kind of doing a lease side-by-side comparison. And then kind of that question that Matthias beat me to the punch too is the contacted OOP versus geological OOP. So we've scratched our head here at Apache. The percentages are lower than what I guess we would have probably thought, but I'll kind of show what we have and where we thought it could go. But I think this will be the perfect setting to kind of expand on that and see what people see across different plays. So I'm going to be talking about one lease today. Brian, again, beat me with a couple leases to show. That's awesome. So the lease I'll be talking about is when we did a spacing trial. So we co-developed 8 wells together. We fracked it at kind of a standard frack of 50 barrels a foot, 1,700 pounds per foot. On the west half of the lease here, we were drilling them at 10 wells per section spacing. So that's 530 feet between wells. The east half was drilled a little bit looser with 8 wells per section spacing, 660 feet between wells. We do have a child well, which I've excluded for today just for simplicity, and it was drilled by a parent well, which again is excluded from today just to kind of leave it simpler. And then also what's nice in the Permian for this reservoir anyways is that we have 180 feet of pay with strong frac barriers above and below. So this is a case where we don't have kind of a huge stacked area where it may be hard to determine your H piece. At least here we can say we think the H is very contained, and we'll see what we contacted within that height. So kind of the workflow we look at it, and again, Brian kind of looks like got to the exact same workflow, is looking at the LFP and the OUP match for each well, but not really looking at it by a well level, but kind of aggregating it up to say, what do certain designs look like? Because individual matches may be a bit noisy, maybe there's communication between wells, but we find when we roll it up to a lease scale, that's where we really kind of get strong learnings that we can rely on. And as we think about what we want to do next, it's really not, we're never doing individual wells. It's what is that next design for the lease. So that lease average is kind of what drives our economics or comparisons anyways. So I won't get into it too much, but this is kind of a look through the numerical RTA for one well here. So yeah, again, matching on LFPs, gas for this one is a little trickier. That's actually why we included in the JIP, was to try to see if there was something we could do. But in general, just kind of individually matching the LFP, the OUP. We look at the LFP OUP ratio a lot, just kind of as a sign of how intensely we stimulated that. So high LFP OUP is really intense stimulation. But just to kind of get a match for each of the wells, and then the goal is to kind of roll them up together. So this would be all those RTA matches, numerical RTA matches rolled up. So I have the LFPs kind of on the top here, the oil in places contacted on the bottom. And what we can do is roll it up to see, okay, at that tight well spacing versus the loose well spacing, are we seeing any differences? What is that kind of marginal gain from extra LFP and extra oil in place? And then how do we compare those looking from lease to lease? So the same numbers here are going to be on the next slide, but just in a table format, which some lovely conditional bar formatting, which I love. But really, kind of, as I said, we roll it up by, we have a match for each well, but we're kind of rolling it up to see what does that total lease look like. So if we look at it on a well average, this is the kind of the average of the 10 by interior wells. So they generated an average LFP of 190,000. The contacted OUP was 1.35 million, so not very large. And then when we look at the 8 by interior averages, we're getting an LFP of 215,000 and a contacted OUP of 1.9 million. So right away, as you could kind of expect, the 8 bys generated a bit higher LFP, but especially they got a lot higher OUP with that looser spacing. Maybe a different way to frame it that maybe kind of makes more sense, again, when you're looking at it from a lease perspective, is if I take these 10 by average numbers and just say, okay, if we drilled lease after lease and taking this number times by 10, I would get a kind of a lease scale LFP of 1.9 million. And if I take this OUP and have 10 wells with that, the lease as a whole would be accessing 13.5 million barrels of oil. We can do the same thing with the 8 by, and you'll start to see some interesting aspects that we use to compare lease to lease for either different spacings, different frac designs, or different geometries. So in this case, the 10 by did generate more LFP. You generated 10% more. But that's not awesome, given that you had to drill 2 extra wells or 25% more wells, and you only got 10% of the LFP extra. So definitely seem to be on the marginal returns for generating LFP. And interestingly, for this lease, we actually would have seen a reduction in OUP. In practice, I don't think that's the case. There's obviously errors on these oil in places for each match. And as you can see, our edge well had a larger OUP. So in general, I would say they probably contacted similar, maybe it's noise in the matches, but you can kind of see it would be very hard to argue with this, that the 10 by contacted more oil in place. So whatever oil in place we were going to contact in these sections, 8 by was enough, and 10 by you could at best argue was the same. And in this data set, it was actually slightly less. You can kind of, I have the 1-year cum and 3-year cums that kind of show the same story. We're really, in this case, not getting much more out at the 3-year marker. So again, just kind of collaborates the story that whatever was here, we accessed it with 8. The 10 by we added, we did not see an extra OUP, and that's going to play a part into kind of looking at that petrophysical oil in place, because if there was extra oil to grab, you would think that the 10 by would have been an increase over the 8 by, and we're not seeing it here. And then finally, just a couple pieces. We do see things like the GOR is obviously higher than the 10 by. You're going to see that in the numerical RTA as a helpful piece. And that does play a role in the economics to some extent, especially with gas at about $4 now. But it kind of just all comes together, and those higher LFP OUP ratios are going to give you higher gas. The LFPs are going to be more correlated to 1 year. as Matthias said. But for this case, since they were all very tight in general, by 3 years, you're really seeing kind of the boundary dominated pieces, which we're kind of seeing as a maximum in this 13 to 15 million barrel total contacted range. So kind of like Brian did, we'd like to compare different leases then, where you're not looking at individual wells and trying to discern what's the impact of each one. So I don't really have numbers here. I'd love to kind of add some more as we see other people's of what they're contacting. And I think it'd be really neat to see if this varies by play type or thickness, those sort of things. But again, we kind of see our contacted OAP plateau at a certain well spacing. So as you go tighter, you're not actually able to contact more oil. We do generally not see a hard plateau, although we see a diminishing returns on the LFP side. So you're always adding LFP. It's going to increase those early time performance, but it's going to make it tougher and tougher for that to economically make sense if not only are you generating marginal units of LFP, but you're not contacting any more oil. It's going to make it difficult for that to meet economic criteria of any variety. And that allows us to compare different leases. So for some, like in this case, we can say the 10 by generated 1.9 million of LFP. It will give it credit for maybe contacting the same oil in place as an 8 by, although as you saw, that was actually, it was slightly lower. So we're giving it credit on the OAP side. But when we run this through any economic style of NPV, PI, or even recovery factor or total recovery, there's just no way this lease ever wins economically. You would go with this 8 by lease, even if you were targeting NPV. We can look at other leases that had, say, different frac designs, looser well spacings, and again, come up with, okay, if your goal is not NPV, but maybe profitability index or rate of return type metrics, then there could be a different lease. Maybe you want to meet halfway through with some criteria. This kind of allows you to look at, okay, what are the different frac designs and well spacings generating for LFP? What are they generating for OAP? We can use those to compare and optimize and then present those best, call it economic frontiers going forward for development. So that was the first piece. The second piece, which Matthias kind of led into, was, okay, if we look at this from a geological or petrophysical side, and we put in the values that we think we have, we would get to an OAP per 640 acres of 27 million barrels. However, when we added up all those wells and scaled it down to 640 acres again, we're only getting 11 million barrels that we would say was contacted through RTA. So our efficiency or some form of contact is only 41%, which at Apache at least we were puzzled at. This seemed low. We weren't super happy. We kind of tried to see if we were making mistakes somewhere. I wouldn't expect it to be 100% for sure. And kind of our mental model is that in RTA or any model type thing, you generally assume that you have full XF in both directions and you have a full height as you go out on that XF. So even at the tip of your fracture, you're getting that full height. And then when we look at kind of how uniform the fractures are, generally the assumption is pretty uniform, not a lot of bald spots that we're missing. We all know that that would be kind of the perfect world at the total end of a spectrum of what we could maybe accomplish. In reality, if we've ever seen models, they generally have uneven XF, so growing out in one direction with stress shadowing. Definitely have a decaying height with XF. So you're leaving kind of a bald spot if you're looking at this from a gun barrel perspective. And if you have any unevenness in your fractures, you're probably leaving bald spots on an aerial perspective as well. So you have two things that are going to lead you to having an efficiency less than 100% for sure. Although I wouldn't have thought it'd be as low as 41%, even when you can see we're piling wells in from 8 by to 10 by that you'd think would have got everything we could have, kind of as a limiting bookend case there too. So some different things we've tossed around at Apache, and this is what I'd be very interested to hear others, is A, what kind of efficiencies do you see? If they're larger or smaller, do we think we have errors in porosity or SW on the Apache side? Are there differences in hydrocarbons that are movable versus ones that are maybe in pores that are not connected? That's some arguments we've been thrown around, but harder to quantify. Clay-bound water is one that our geologists talk about. I know for oil, by moving kind of the rel perm endpoints to the left or the right, you can change the matches will look the same, but you'll change what percent of the OAP you'll be matching at. So that's one we've toyed around with, but it's not a big mover and not big enough to change it dramatically that we've seen. So a couple of different things. We don't have a great explanation for why these are in this range, but maybe that's just the way it is. If you look at different plays for oil and versus gas, we'd be really interested to see how other operators are handling that. So kind of the questions I would pose to the group is everyone seeing this kind of efficiency? It looks like Brian was seeing numbers in a similar range, so that actually makes me feel a bit better. I'd be curious if gas is different than oil. I could see gas being easier in a way. You don't have to worry about the rel perm piece. Really, you got higher mobility, so maybe some of those bald spots do get eventually drained. So I'd be, I guess, as Matthias showed in the survey, it does look like there is a delta. So I'd be really interested to see how that works out. Porosity, movable hydrocarbons, are the Apache geologists doing what geologists do best? Where we were kind of wondering if there was just some flaw where even looking at different areas, maybe there's a geological bias by who did the work there. And then finally, if we do say we're happy with that, if we're looking at different well or frac designs going from, call it tight well spacings or different cluster efficiencies, is there a way that we can improve kind of the LFP or the contacted OAP? And then thinking that will probably lead us in an economically optimal direction if you can contact more of that without adding that much extra cost. So
yeah,
I know that
perfect.
was, yep. So I guess I'll end here. Just we think it works best by aggregating at a lease level instead of a well-off level. We see that haircut that Matthias talked about. And if you have any other feedback looking to compare leases, definitely be happy to do that because it's something that we've scratched our head about here at Apache. With that, I'll hand it to you, Matthias.
Awesome. So we have a bunch of questions here and a lot of good comments. I think just the first question from Seth from Hess. So he just wondered if the completion design for the 10x and 8x was the same. Sorry if I missed that, he said.
No worries. It was the exact same. So the completion, yep, same loading, same clusters, same everything. This was meant to be a sole spacing trial.
Yeah, perfect. And then this rough trend slide that you had there in this one, so it comes from Manuel as well. That's exactly the same behavior that they see as well. Would you like to elaborate a little bit on that, Manuel?
Sure. Hi. Yeah. So we do these types of studies all the time. In our business, we're a mineral business, so we do this for all the basins with public data, and we see that. I mean, we used to think that as you put wells closer and closer, you hit a plateau that you can't go over, but we started realizing that even in really, really tight spacing, sure, your EUR per well goes down, but the spacing is so aggressive that your total oil, as we call it, or total lease contacted OIP, as you call it, actually keeps going up until you are very, very close. So that was very interesting that you came to the same conclusion with operator quality data.
Yeah, for sure.
And then we have a question just from Gustavo. Just you talked about the LFP OIP ratio, and I'll probably throw that around a little bit. But I think for some people that terminology might be a little bit new, but it's just A root K divided by oil in place, could be potentially gas in place or pore volume for that matter. But it's what's the physical meaning of that ratio, and how do you kind of think about that, whether that value is high or low? What does that say about your well performance, if it's good or bad?
Yeah, so I think that's a ratio we use a lot. So kind of the way I think about it is that the smaller your LFP OAP ratio is, that means in one way or another you haven't stimulated your volume that much. So you either haven't added as much fracs, cross-sectional area, or you just have a low perm where for that rock volume you're not stimulating it very effectively. So we see older wells, typically at suboptimal completions, have low values of LFP OAP. As we go into either bigger fracs or tighter well spacings, that value will increase. And that you can kind of directly translate high LFP OAPs are going to mean very quick to boundary dominated flow, very quick to rising GORs. And it's also going to affect other ratios. Like if anyone's a fan of EUR to 1 years, the higher your LFP OAP ratio is, the lower your EUR to 1 year, because you're just getting that volume faster. And if you see values at very low LFP OAPs, then you could have a larger EUR to 1 year ratio. So I think it ties a lot of the aspects, and wells that have similar LFP OAP ratios are going to behave similarly for GOR decline behavior. They just may be different by an absolute basis of LFP.
Great. And then just this about one of the plots from John from Birchcliff there, how did you generate the group OIP versus spacing and the group LFP versus spacing?
So not sure I 100% understand, I guess, but we'd roll up to say we have an individual match for each well. So treating it on well by well level, but then for whatever we think is kind of a design. So we'll typically do leases in either half, or we'll be comparing one lease to another. And what we see the value is kind of summing all the LFPs and then summing all the OAPs of a particular style. And then we'll compare that style for metrics like how efficiently did we generate LFP or LFP per capital cost? How efficiently did we contact the OAP, or call it contacted OAP per capital dollar spent? But we see kind of that summed level giving us much better conclusions than, as you can see, when you're looking at it on a well by well level, there's a bit of noise in how those matches are exactly. So the lease level to me just makes a lot more sense.
Awesome. And then the last question before we take a 5-minute break is a question from Dave. And that's probably about this comparison between the contacted and the in-place pore volumes. So when he thinks about unconventional rock, it's hard for him to imagine that all of the pore space is hooked up in one continuous network. So that could potentially be a part of the issue, and I think that's a good comment there. Any flavor to that, Braden?
No, I agree. I think there's a lot of things that kind of 100% would be ideal in every single thing. And if it's not ideal as you go down the list, to me, it's like not ideal multiplied by not ideal multiplied by not ideal. 40% still seems low, but it does make me feel better that other people see those ranges, so that we know either we're not terrible at contacting the oil we have, or that our geologists aren't crazily out to lunch, at least on this.
Excellent. Kadok, Mo, any questions?
I just had a quick question regarding if you've thought about for example, the frac height. And I'm mainly thinking about the fact that when you're adding more wells, you're actually supposedly filling more of the space horizontally, but you're not seeing more contacted OIP. While so it makes me think immediately of is it something with the height maybe that we're not actually contacting all the height, the 180 feet that your geological model is talking about?
Yeah, it's definitely possible. Kind of our mental model would be that if you space them closer, if you have any stress shattering, we thought that might have given us more H. There could be competing arguments where as you start to interfere, maybe you're leaking off into the other fractures so that you inhibit it. And then part of the other piece here was we have that 180 feet. There's strong frac barriers, but if you frac into that, maybe you are technically generating AC, but if you don't have any perm or hydrocarbon pore volume there, from an RTA perspective, it's meaningless. So fracking into something that's not productive, the completion engineer maybe did something effectively, and it's just we didn't put that in the right spot from a reservoir, so you don't see it. So definitely a lot of potential complications with the HXF pieces for sure.
Matthias, could I just ask one quick question?
Yeah.
The barrels that you're talking about, all of these barrels mapped and barrels contacted, these are stock tank barrels of oil, or is the gas being considered in any way?
No, this is all be converted to stock tank and it'd be undersaturated, so no gas phase to start.
But I mean so the gas production and the gas in place, it's just really not included at all in this analysis.
kind of, I guess. We would, so we would get to, like, this OIP would be our match from the numerical RTA, which would include obviously the gas piece to help constrain in, and we'd have a higher recovery factor within this volume of gas versus oil. But I don't think we see the gas side kind of saying you're blowing this volume up to have something closer, if I understood the question there. But it may be something we can think about further to see if the gas side would be have a different answer for that efficiency factors. Is that kind of how you're thinking?
Just not sure what these are barrels of oil.
Yep.
And the gas is not being included at all from these numbers here you're talking about, per se. Correctly.
No, yeah, they only included in as far as the volumetrics or the numerical RTA, but not
Right.
explicitly. Yeah.
Okay.
Awesome. So we'll take a 5-minute break, and then just after the break, we'll have one presentation just talking about analytical RTA versus numerical RTA, and then Mo will talk about some early time noise in the diagnostic plot and why, or the reason behind that in the numerical RTA workflow. Thanks again, Braden. Super interesting stuff. There's a lot of good, interesting things I think we can probably take here as a group also when we go into the next phase of analyzing this, and maybe doing that comparison as a group could be fun to just compare the mapped in place numbers versus what we derive from our workflows. Okay, so we'll be back here in 5 minutes, and then in the meanwhile, if the next presenter can just share their screen and we are ready to go. Okie doke. So I think we'll get started with the last presentation here. Actually, remind me just to set the stage a little bit here as well, Tison, before you show the presentation. I'll just show a couple of slides on this topic before I'll leave the floor to you, just so we have everybody in the audience on the same page before we get started. Okay, so I'll just show a few slides and then we'll turn it over to you. So what we're going to discuss now is basically just the difference between analytical RTA and numerical RTA for a field case, and we need to ask ourselves what is actually the difference between the LFPs that we derive from an analytical and a numerical RTA method, and we discussed that a little bit earlier today. The fundamental thing that we like to assess is, okay, if we go into any reservoir and we have completed it and it has a given surface area and it has a given contacted pore volume that we've been able to contact with our completion, the A root K should not be a function of the fluid, especially if you use that to compare wells across for completion efficiency or frac design, etc. Because as a completion engineer, your job is to deliver fluid, and it's the petroleum engineers and geologists and petrophysicists' job to find oil in a sense. So if you only want to evaluate the completion, then it's a more fair comparison, of course, to compare LFPs that are fluid agnostic. So what I'm trying to say here is that in other words, no matter what ratio of oil, gas, and water you have in a well and what the well is producing, you should get the same A root K derived no matter how you fill up that pore volume. And we can look at a very quick example before I'll turn it over to Tison here in a sec. So if we have an example of a rock that we filled up with around 7 million reservoir barrels of oil. And then we fill that with different ratios of fluids in three different simulated examples. So in the first case, we do 20% water saturation and 80% oil, and then we decrease that down to 70% water saturation and 30% oil in the third case. And if we go in and look at analytical RTA for these just synthetic cases, when we have very little water in the model, so case number A, we get a LFP that's very close to the true LFP. The numerical RTA gives us exactly the LFP that we're looking for, 450,000 in this case. If we look at case number 2, where we have 50% water and oil, the LFP from analytical RTA is 2,000, while the true LFP is 4,000 or 200,000, while the actual LFP is 450,000. And in the last example, just to show that in its extreme, the LFP from analytical RTA would be 90,000, while what we're dealing with still in numerical RTA is a true total LFP 450,000. So if you use analytical RTA, you should at least use it for wells that are producing with a very similar water cut and have a very, very similar PVT for that to be a true, consistent apple-to-apple comparison when it comes to productivity. So just to summarize, analytical RTA results like a single phase LFP, if you like. Numerical RTA results in multi-phase LFP or a total LFP, and in general, that LFP should be larger than what we see in analytical. For this to be true and for us to honor this in practice, we should try to match our water cuts in the numerical RTA workflow, at least stabilized ones. So a good consistency check that we looked at earlier today is to make sure that the LFP from our, this is the wrong way, but the LFP from our numerical RTA should be higher than the ones from the analytical one. And on that note, I'll leave the floor to you, Tison, and then I'll just mute myself here and looking forward to the presentation.
Hey, good on everybody. I think this is a real example. It's kind of like complementing what Matthias has spoken just now. Let me start with this context. I think innovative is that we have been using Harmony for quite some time. We have a huge database on Harmony. Of course, it's based on conventional RTA. So the questions, we are kind of new to this NRTA. So questions that I always ask myself, there are two things, right? How does it differ and versus numerical RTA? And of course, there'll be difference, but does it really matter? Because in the end of the day, you are looking at the relative performances. You're looking at relative for instance, a square root k. And the second question is, how it is going to aid my development, right? So I think in the company we're using very different kind of tool sets, from analytical to simulation model to observation or conventional analysis. So we would like to bring an RTA to our toolkits, and then seeing some of the examples shown by our colleagues just now, I think I get some of the good ideas. So I probably want to pursue more on that. And the intent of these two slides is just to give you some of the observations that we have just very recently. So in this case, we have two wells, C1 and C2. Good thing about this is that it was developed, these two were developed in a similar DSU. So, okay, you can normalize the geology. And C1 is kind of like, sitting next to a larger parent or have a higher cum. You have a low initial PWF just based on the interpreted PWF from Dex and Brill. You have a higher water cut because it probably needs to produce some of the remnants water from the old parents, and then they have a lower oil. Well, C2, this is a larger spacing versus parent. And by looking at using harmony, is like, oh, yeah, we're going to have like 24 times the ratio A square root K. And I have to say that a lot of time, I like to use A square root K because it is similar to the KH in our conventional classical reservoir engineering, right? KH is always a lump term, so it is amalgamations of KH is easy because a lot of time you can know H, but A square root K, it has a very different complexities because you very difficult for you to dissect what is A means from HX to XF and also the NF. So I use this to tell me about, what is the completion efficiencies. Of course, you can argue that we can use the PI for us to do this, but a lot of time a PI is, it is a bit haphazard for us to look at. So looking at this, I know that it cannot be right because the job size for well C2 is probably like 40% better than or higher than C1. It cannot have a ratio of 24. So this is telling me that I have very limited fracture geometry, so it's not realistic. So by using an RTA, you are probably getting 2. I think this is about right because C2 is larger than C1 by about twice. And talking to Matthias, I'm also using the minimum contacted pore volume, and the ratio is about 2. So using minimum contacted pore volume in conjunctions with the A square root K derived from the NRTA, it's kind of doing a cross check. So I think we are getting a better frac solely because of the last jobs, right? This very simple exercise just to give us a flavor of what does it do. But if I were to have a set of wells, all of them are producing a 50% water cut or 30 or 40 to 15% water cut, do I still see the values of the NRTA in my understanding? Because the basis is the same, right? In this case, it is kind of like stand out because one case is having a water cut of 90% in the early days. This guy is about 40%. You see the distinct, but when you have a group of wells, all of them are producing more or less the same. I try to find what is the incremental values of this NRTA to my work, because in the end of the day, I want to know how I want to develop my future DSUs. And whatever DSU I learn from here, can I kind of like, apply to the future DSU right away? Maybe not. So some of the questions that I want to ask everybody would be incremental benefits NRTA versus conventional RTA. For me, A square root K is indication of completion efficiency, much like the KH. To me, having the right A square root K, is that important? Yeah, maybe. But I think relative A square root K amount of wells are probably good enough a lot of them. And whatever, the XF and KM or probability generated from A square root K, I will look at it with a grain of salt. I think it's indications, but you never be done because NF is a very huge unknown to begin with, right? So back to the most basic question, how RTA can aid development? I think we have quite a good 2 or 3 presentation just now, kind of like, talking about along the same line. I think I want to digest a little more on that, yeah. And one question I want to ask everyone is that when we drill and complete well C1, because of the proximity to the parent it has a lower PWF. So in this case, it's about 6,000 versus this guy is probably like 8,005. So for PI, I will use the maximum PWF, which is 6,500 PSI, as the input initial pressure in the software. Is this a common practice for you all? Or you still put in virgin pressure? To me, this is the right ways to do, but looks like everybody would have a different opinions on this one and different thoughts. So I just want to kind of like, extract some information from everybody. How you would typically do that? Because right now, with tighter and tighter spacing, more and more child wells, this is the problems that we're going to see more and more. So in order to be standardized, I think we need to have a very definitive way and standardized way of doing this.
Yeah, very good, and that's a great question for the audience today. So basically, if you have a parent well that comes in with, let's say, 8,000 psi virgin pressure, and then you're putting it in a child well, and the maximum bottom pressure that you can calculate for that well is 6,000 because of depletion effects and whatnot. Like in an RTA exercise, a single well RTA exercise, should you still go ahead and use 6,000 or 8,000 as the virgin pressure for that analysis, or should you use 6,000? Dave, I don't know if that's what you have a comment on, but I would love if it was that, or if you have another question, feel free to shoot.
Well, no, my question and comment is along these lines. So, Matthias, to what you're saying is for RTA, I think on a child well, I mean, it's very important, and a lot of analysis hinges upon that initial pressure. And so for a child well, you want to get the initial pressure of that child at the time it was drilled. And so one technique I've used is after completion, testers are on site and you have very detailed high frequency flowback data. So I've used the technique of looking for the calculated bottom hole flowing pressure when hydrocarbons first starts to show up, and use that as an estimate for the initial pressure on a depleted child well. So I maybe want to throw that out for comments. Are there any pitfalls or whatnot to using that technique for estimating initial pressure on child wells?
Yes, I think agree, because that well, when it starts to produce, this is what it felt, right? It doesn't feel whatever virgin pressure that we typically use to kind of assign to the well. Yes, yeah, it's like maximum PWF. PWF is the calculated numbers, is the input numbers. I think I will use that.
Very good. And over to just Dave's, or there's a comment on your question there, Dave, as well. Brian, that had a presentation earlier today. This is exactly what he's done, and has done it for a long time. I think probably Steve Jones, that was in Cimarex and Bravely Newfield at the time, also presented a paper suggesting that way back. Maybe he's not the only one, but I remember I think I read that, and I think it's something that I've seen a lot of people do. So I don't know if other people have comments along those lines, just to pick initial pressures for these child wells. Braden or Barry or someone.
Also, any comments, if I can add just quickly, if any comments about the initial pressure, the fact that you're charging the reservoir with a frac water, so that initial pressure as well.
Okay. No further comments. So, are someone using the virgin pressure for these child wells? Or is everybody trying to kind of find a new PI that's representative for that well and accept that it's depleted and it's not what it was in situ?
I would say on our end, we've tried both. We typically like to keep everything constant, rel, perm, properties, and PI, and then we just say a child well has a lower LFP. And I think that's comparable in some ways, but it's probably not as physically representative of its. So I can see it both ways, but we've gravitated towards saying it's a reduction in LFP rather than a pressure change, but definitely see it both ways.
Okay. The thing that I've seen then is like it looks like your well has a low FCD then if you have a big difference between your PI and your PWFs, I guess, which you will have in this case, which might not be a real thing. So yeah. Oh, that's good stuff. Something to think about. I'll include it in the next survey for sure. Thank you so much for the presentation there, Jiswan, and I think this is something we can investigate even further. The last topic that we'll have is Mo presenting on some of these early time LFP trends and some of the uncertainty associated with that. That's going to be the last presentation today, and we'll send out the presentation recording either tomorrow or on Friday, with also the summary of the Q&A as well there. So Mo, feel free to get it started.
Yes, sir. Oh, sorry, I was muted. Can you see my screen now?
Yeah.
Yeah. So as Matthias has said multiple times, I'm gonna try to talk about commonly observed LFP trends. And my name is Mohammed Dahouk. Everyone knows me as Mo, so just call me Mo if that's if you want to refer to me. So why are we here? We want to talk about Bowie and about LFP, but not in the way you're thinking. It's not. We're not going to talk about Braden, even though I'd love to do that. We're going to talk about the Bowie diagnostic plot and how the LFPs can look in the Bowie diagnostic plot when you're working with real data. And the reason we want to talk about this is because we see this every time we're going to analyze a well and we go to the Bowie plot. We will see either an LFP that, like what I like to call climbing up, that's coming up and trying to basically climb in towards a stabilized value of LFP, or an LFP that's going down from a given high value. In my experience, at least the cases that I have looked at, 90% of the time I'm looking at the plot on the left where my LFPs are actually climbing, and basically the other 10% of the time the LFP will be coming from above the stabilized trend. So to try to understand why this is happening and when can we see these trends in the LFP plot, we need to go back a little bit and remind ourselves of the theory. And that theory is basically what was presented in Braden Bowie's paper of the Bowie workflow. How we come up with that LFP plot is that we basically take the ratio between the actual measured rates for the given well. So you take the rates for your well, and we divide those rates with an infinite acting model that is the model that we're using in the numerical RTA workflow. And that ratio will result in something like this. That's how what the theory would look like. But in reality, actual rates don't look like this, but more like this. This is what we see, and that's mainly because of the flowback period where we're getting very little oil or hydrocarbons flowing back, and then that will basically automatically result in our LFP plot having the same trend. Okay, and just so it's not only cartoons, this is an actual example from the SPE data repository, well number 4 in the Eagleford. And if you look at the early time data, you'll see exactly what I'm talking about. And you guys are very familiar with this since you're actual operators. So you see in the very early time, you only have water rates actually for the first maybe 8 or 9 days, and then suddenly you start getting oil rates, but that they take still a couple of days before they stabilize. And this is the trend that I'm talking about, that your model, when you're running the model in the numerical RTA, the model is actually not going to be accounting or it's not going to have the same behavior. Your model is going to be producing based on the bottom hole pressure that you've given it, and basically producing hydrocarbons from the first day. That's what is going to make your LFP plot look like this. This is actually the LFP, the numerical RTA workflow applied to this well. So you see, if you look at the early time, you'll see that the LFP is climbing up, and that period in which the LFP is climbing up is basically directly correlated with the period in which your water cut is not matched. And that period in which your water cut is not matched, at least the way we like to think about it, is the period in which you're still flowing back some of the frac water, and that's why your model, since you're not actually injecting that frac water into the model or simulating that part into the model, your model will not capture that, and therefore your modeled rates will be higher than the actual rates, and that will result in your LFP climbing up like this. Okay, so this is the way the LFP will look like in 90% of the cases, and in 90% of the cases, it's going to be because of the fact that the model basically, the well is charged with water, and it's producing only water for some period, and then when it starts to produce oil, or gas, it starts to produce that very slowly compared to what you will see in a model where you start producing the hydrocarbons from day one. But in addition to that, there's other things that can actually affect your LFP, and that actually is very related to discussions we've had in the previous presentations where we've talked about this. So what can affect my LFP? It's basically anything that would make my model rates be larger than my actual rate. And that's again a reminder to the theory of how we come up with those LFPs, how the numerical RTA workflow works. And basically what we're going to focus on this presentation is on two important aspects that would make your model rates larger than your actual rates. That's the initial reservoir pressure and the FCD that I mentioned is fracture conductivity. So very relevant to the question that was asked in the previous presentation. So first, we're going to study the effect of the initial reservoir pressure. And for doing that, we're going to look at the synthetic well. So we're going to do a reservoir simulation, which is a full physics reservoir simulation. A well that basically is flowing now here for 10 years and has a GOR of 1,000 SCF per stock tank per hour. And we're going to take this well that has an initial reservoir pressure of 8,000 psi, and we're going to run it through the numerical RTA workflow, and we're going to increase that reservoir pressure to 9,000 psi in the numerical RTA workflow. So if we analyze this well, assuming that the initial reservoir pressure is 9,000 psi, this is how the LFP plot would look like. And this is basically simulated data, so the LFP plot is supposed to look perfectly or match perfectly with the actual production data. So you see here, and this is back to what Matthias was talking about, where you're going to get a signature that sort of tells you here you have 500 days where you're below your LFP for the well, and during those when you see something like this, we're going to look at that in the next slides. It can give you the signature looks like it's a low FCD well, for example, because your production is much lower than the model production. Okay. If we took this same well and now instead of analyzing it at 9,000 psi, we did that at 7,000 psi. So we assumed that the reservoir pressure was 7,000 psi instead. We see the opposite behavior where we get the LFP coming down like this. And in that case, that's also what we would expect, because basically the model is producing less than what the well is actually producing. And the reason we're going actually through this presentation is because I actually have seen this signature in a couple of wells that I have analyzed with some of you. So it's important that for you to remember when you see these things, what they could be meaning. Maybe if you have uncertainty in your reservoir pressure, that adjustment in reservoir pressure would bring things at least to make more sense. Okay, and just to remind ourselves, if you actually had the correct reservoir pressure, everything should have matched straight from the get-go, and that there wouldn't be you wouldn't have the shooting LFPs, climbing LFPs, or declining LFPs every time. Okay. And now to the second part of the second aspect that we will study is also the effect of FCD. Should be very similar to the reservoir pressure, but it's important just to differentiate between those two. Basically, this is the numerical RTA plot for the Bowie diagnostic plot for the SPE data repository well that we talked about. And if I took this exact same well, but just lowered the FCD in my numerical RTA analysis, just you can see here how basically that the period in which my LFP here is shooting up will become much shorter. And in this case, you might think, okay, this looks like a better match for this well than the infinite conductivity case. So this is the infinite conductivity case. This is if I apply a lower FCD. But the thing is, if I do this, then I get a very poor match of the rest of the data. So in this case, it wasn't the best to apply it, because we've seen before that this LFP shooting up period was very correlated with the period in which we didn't have a good match of the water production. So to study more of the FCD cases, I made a synthetic case where I basically lowered the FCD. So I took the exact same reservoir simulation model, full physics simulation that I had studied before, but I just lowered the FCD now. Instead of infinitely conductive fracture, I made a fracture, an FCD of, I used an FCD of 5. And then I took the results from that model and fed them to the numerical RTA as production data. And now with that as production data, I ran the numerical RTA analysis with an FCD of 1,000. And you can see here that I get basically 3,000 days of production, almost 10 years of production, where my FCD is, sorry, my LFP is still shooting up. And this is very clear signature. If you're seeing this in your data when you run the numerical RTA workflow and you're looking at the Bowie diagnostic plot, and then you see that the cumulative LFP is climbing up for a large period of time where you're already matching your water rates, then it's a very good signal that you should be using a lower FCD. And that's actually what Brian was talking about earlier today. If I use actually a lower FCD, I just wanted to show that instead of an FCD of 5, which was the original FCD of the well. If I used a lower FCD, I went down to an FCD of 1, then I would get this a similar effect as when I lower the reservoir pressure, where basically my LFPs will be higher than the actual LFP that I picked for the well. Okay, and just a reminder to all of us that if I had used the correct FCD, then I should see the correct, the perfect match in the Bowie diagnostic plot. And many of you actually might have observed that even in the perfect scenario, so this is a perfectly simulated scenario, in the very early time, you might have some oscillations, and that just due to the numerical simulation. So when the models are being run, the first days you might have some instability in the rates. Mainly because the fracture is initialized with a different set of relative probability curves than the matrix, and that first period is a little bit unstable. Okay. Yeah, so that's the FCD and the initial reservoir pressure. And then we have a final comment that I would like to make, and that's related to using cumulative LFP versus instantaneous LFP. And that actually is just an option that you have in the software in Whitson Plus, where you can click this button right here to use the cumulative LFP, or to just, if you tick it off, then you can use the instantaneous LFP, but you can pick a moving average, so to try to smooth it a little. In theory, both of them should show you the same results. That's what you're seeing here. This is a simulated case. in practice, the cumulative LFP actually helps us remove a lot of the noise. So this is the SP data repository well that I was talking about. If I looked at it in cumulative space, you see this is how smooth the data would look versus if I used the instantaneous LFP. So in general, we like to use the cumulative LFP because it helps us remove the noise. It makes the analysis much easier to the eye, much easier to show to your manager, etc. But it comes with its caveat, which is that the cumulative LFP will be delayed because of basically what we talked about, the early time climb in LFPs. So the cumulative LFP will be delayed in kind of catching up with the model, and that can lead to very misleading results. Let's say if your cumulative LFP, if you're looking in cumulative space and it is still climbing up, then we had the tendency, let's say you might have the tendency to take and match the LFP at the highest point here. And what we would recommend in that case is to not use cumulative, but to go into instantaneous LFP mode. And you'll see that there you'll see the real LFP, hopefully a more stabilized. So you see here at 30 days already, we're getting a stabilized instantaneous LFP, while here we're still at 80 days, not even getting to that point in cumulative space. So it just takes more time to kind of catch up in cum space. So we need to be careful with that. And this is, I actually, the first times I did the analysis, I was a victim of using the cumulative LFP and kind of moving the LFP of the well down to that line. So it's important to keep that in mind. That was my presentation. Just quick concluding remarks. So wrapping up the whole thing, the early climbing LFP behavior is expected whenever the production from the model is going to be larger than the actual production, and that will happen while the well is producing at decreasing water ratio. So when you're still flowing back some of the injected water, when the FCD of the model is larger than the FCD of the well, so that means that you have to adjust the FCD in your numerical RTA down, or when the PI of the model is larger than the PI of the well, or the initial, I'm talking about initial reservoir pressure in this case, and that is the same. You need to adjust your initial reservoir pressure down again. And finally, just remember that cum LFP is not always equal to instantaneous LFP, and just take that switch and check it out.
Great, thanks, Mo. So it was funny because Jordan had some questions about what if we did this with instantaneous LFP while you were presenting. So that was good that you had a session on, or a special session on that. And if that didn't answer the question, Jordan, just feel free to ask it again. Yeah, that was actually something I was thinking about as well. Like, this is a great question from Stephen. Would it make sense to have an option to not include the first X number of days in calculating the cum LFP?
Yes.
Yeah. So can you write that in the backlog, the software backlog, Mo? Just as I think that's a great suggestion, Stephen.
Yeah, that makes a lot of sense, and actually something, I hadn't thought about that specifically, but was trying to think of a solution for that cum LFP because it's so clean, but at the same time it can trick you if you only have like 100 days of data. So yeah, makes a lot of sense, Steve.
Perfect. So on that note, we're 3 minutes over time. We'd like to thank everybody for the presentations and contributions and questions today. The recording will be distributed. The presentations from the presenters that would like to share their presentation will also be provided, and that will be sent out in the next weekly update email now on Friday. And on that note, if there's any other questions or follow-up ideas or feedback or anything related to the software or related to the workflow or the JIP, feel free to ask us over email, or for those of you who are in the States, just call me on my phone. And except from that, thanks Mo for the great presentation, and thanks all for joining.
Thanks everyone.
Thanks.
Thank you.
Thank you.